ठीक ठीक. हेलो गुड मॉर्निंग सर. गुड मॉर्निंग सर. सर आपका माइक बंद है. माइक.
Good morning, Atul sir. Good morning, Purva sir.
फाइन सर. एवरीथिंग इज फाइन देयर ना सर.
Yeah, everything good.
ओके सर. ठीक ठीक.
Sir, Atul sir,
Yes, sir.
do I have rights to share my PPT?
Yes. Sir, go on the present mode.
Present mode I am going, and a window should be there, but
Yes. In your box, there will be your presentation, sir. Then click on that presentation and
No,
share it.
no, I tried it, but today I don't know why it is not showing on my screen. Chrome will share the contents of your meet. Okay.
No, just open your PPT, sir.
Yeah.
Open your PPT, then go to present now mode. Just minimize it and first open your presentation outside this Google Meet.
Okay, I
In
already
your
opened it.
window.
Okay, let me again try it.
Just minimize your Google Meet and open your PPT outside this Google Meet.
Just a moment. Now, today, I think there is some problem. Because I use it in my classes also, but today it is not
Okay.
showing me that PowerPoint. But anyway, let me check that where to do it.
Okay, sir. Okay.
Okay, let me try. Yeah. Atul sir, actually,
Yes, sir.
it is application, PowerPoint application. I don't know why it is not showing in this particular thing. I'm not getting that.
Okay.
Okay,
So, Professor Ganni,
yes, ma'am, I am able to open it, and I don't know. In general, it is showing that PowerPoint's available, whatever options, PowerPoint and other options. But for this particular thing, it is not showing. And to go for the present now, there are three options. You entire screen, a window, and a Chrome tab. So I am going with the a window. So in
yes.
this, it is generally showing that PowerPoint, but today it is not showing. I don't know what may be the reason. Choose the
Okay.
okay. Anyway, no, there are some videos. Actually, I could have done it, but okay. Let me try with other way.
Full window.
Yeah, full window.
No, it is coming, sir. Yes, yes,
Now it is
yes, it is
coming?
coming now. Yes, yes,
Okay.
it is coming, sir.
Okay, let me do with this complete screen. It is now sharing with you all. So shall I begin or shall I wait for some more time?
No.
Okay.
Wait a minute.
Fine.
Subodh, are you there?
Yes, sir.
Subodh, okay, you can start now. Na? Okay.
A very good morning to everyone present here. Welcome to the day 3 of FDP on the topic Recent Advances in Mechanical Engineering. Today's session focuses on predictive maintenance of mechanical components, and we have with us here Dr. Pavan Kumar Kankar. Sir, you are working as an associate professor in discipline of mechanical engineering, IIT Indore. Your research interests include fault diagnosis and prognosis using machine learning techniques, reliability, biomedical signal processing, and analysis of dynamical systems. You work with Villanova University and United Technologies Research Center, USA, for effective discrimination between 4 kinds of common defects in gears by utilizing the method of recurrence analysis. Dr. Kankar also worked on improving theoretical model of unbalanced shaft bearing system with researchers of Faculty of Science, University of Yaoundé, Cameroon. He contributed in various projects awarded by national and international funding agencies under Imprint India initiative by Ministry of Human Resource Development and Indian-Japan Cooperative Science Program, etc. Total worth of rupees 3.3 crores. Dr. Kankar, you have established Machine Dynamics and Vibration Lab, Undergraduate Computational Lab in IIT-DM Jabalpur, and System Dynamics Lab at IIT Indore. You have supervised 6 PhD and 16 MTech students. You served as a guest editor for the special issue of Advances in Mechanical Engineering on Advanced Signature Analysis for Machine Fault Diagnosis and Prognosis, 2019, and lead guest editor for the special issue of International Journal of Rotating Machinery on Fault Diagnosis and Prognosis of Rotating Machinery in 2017. You are a fellow member of International Institute of Acoustics and Vibration, USA. You are a member of various professional bodies like American Society of Mechanical Engineers, Society of Reliability and Safety, Tribology Society in India. Your work is having more than 2,000 citations. I would request you to please start with the presentation.
So, thank you, Atul sir and Powell sir, for giving me this opportunity to interact with your department and other colleagues, those who are attending today's session. So, today we are going to talk about the predictive maintenance of mechanical components. So, if we talk about industries, even in the COVID situation, we might have seen some of the incidents happen in South and in other industries also, where there are certain hazards or some unwanted conditions happens. Okay, so all these conditions are indicating that there is some important thing is missing in our maintenance activities. activities. So maintenance is again important because in such situations like in today's scenario when economy is going down and there is a lot of implications of each and every aspect of production. So maintenance is another important aspect which need to be carefully look out so that overall cost of the components or production can be reduced. So in this regard, today we are going to discuss various things including different maintenance strategy. We are going to talk about some of the condition monitoring methods. Then we will talk about sources of vibration in machines. And if time permits, we will be going in some details of bearing fault diagnosis. So with that, let us see this figure first. When we talk about the cost, there are a lot of costs involved in the production, like design costs, production costs, and marketing costs. Then we are having this another important cost, that is maintenance cost. Maintenance cost involves various kind of costs, including warranty, guarantee, our free service, and other things. So when we talk about these costs, there are important data. You can see here that first of all, 45% of all maintenance efforts are ineffective. Sometimes we are doing some maintenance efforts in our vehicles and many other industries. So it is a study which is showing that 45% of these efforts are not proper. They are ineffective in one way or another way. Second is 40% of scheduled maintenance costs are spent on assets with negligible effect on uptime failure. Uptime failure, basically we are trying to identify incipient fault before actually they occur. So we are talking about the condition when we are trying to locate those kind of faults which are about to occur. But it says that 40% of scheduled maintenance costs are spent on these kind of parts, components, or assets which are having negligible effect on these kind of failure. Similarly, another important data is saying that 30% of maintenance activities are carried out too frequently. That means we are conducting maintenance part continuously or with the more aggressively, which is even not desired. So we need to see that how to do all these maintenance activities so that first of all it is effective, it is optimum way we are going to conduct it, and we are going to conduct this maintenance activity for the components which are really having a significant effect on the overall plant performance. So with that background, let us try to see some of the cases. So here you can see a simple case of truck trailer on which there was a wheel or rear wheel, and because of some reason it has failed. Complete wheel is dislocated from the axle, you can see here. And because of this failure of this, there can be a complete damage to the truck. It can also result in the human casualty also. So these kind of failures are very dangerous. So you can see that zoomed view of this, and this is complete wheel separation in this particular case. Second, you can see here there is a paper mill bearing in which there is a failure over here, you can see. So this is the failure results again because of this bearing failure. In third case, there is a piston failure, which is a reason. There is a big end bearing failure, and because of that piston was misaligned and it failed eventually. So all these three examples which we have seen here, and I talked about other incidents happened in India recently. If we look at all these incidents, what all these incidents are indicating? These incidents are basically indicating that there is something we are missing during our maintenance activity. We are doing maintenance, but still we are not that good that we can predict the failures are about to happen and we can prevent them. So we should have certain mechanism, certain way which can do this kind of maintenance activity. So to understand that, let us talk about what are the maintenance strategy at present we are having, or how we can classify maintenance strategy. So more conventionally, if we talk about, we are having a strategy known as breakdown maintenance strategy. So when we talk about the breakdown maintenance, we are talking about the condition in which a component or the machine is done till a particular component is failed or the machine is failed. So we are utilizing it without any maintenance activity in between. So whenever there is a failure, complete failure, we are going to conduct some maintenance activity. We are going to change those failed component and again the machine is going to run with the new component installed. Now, what can be the possible advantage in such condition? So in such condition, main advantage is that we are going to use the maximum possible life of the component. So we are using it up to whatever possible life of that component was existing. We are not replacing in between. So that is the advantage. But what is the disadvantage? There's not a single, there are many disadvantages about it. First of all, we will be having sudden failure, sudden downtime for the plant. Whole plant is stopped for a longer duration. So this is the first disadvantage. Second, now since it is stopped, production is stopped, we need to have that maintenance activity day and night. We need to give we can say overtime charges to the labor. We need to have inventory in hand so that we need not to procure during that period. That is also results in a more downtime. So we should have a good inventory. That will involve inventory cost. We will be paying our worker more so that they can work day and night, and we will be paying them overtime cost and many other costs. So if I look at that, so high spare parts inventory cost, high overtime cost, high machine downtime, and low production availability. So these are the main disadvantage of this method. So even though it is utilizing the component up to the maximum possible extent, but overall cost, if I talk about, that cost is going to be very high, which I don't want. So what is the strategy? I need to go with the next improvement, that is known as our preventive maintenance strategy. Preventive maintenance strategy, if I talk about, it is a very common strategy which we see in many applications, like even in our house, when we purchase any particular component, maybe your bicycle, your motorcycle, your washing machine, or refrigerator. After certain time, we are going with the scheduled maintenance, that is known as we are going for the service. We are going for the servicing of our bicycle, we are going for the servicing of the car and all. Now, advantage is what? That we are going with the whole maintenance process, we are getting things done before actual failure occurs. So overall chances of catastrophic failure, sudden failures are decreased. That is the advantage. But if I look at the condition that when we are going, for example, when I buy a particular vehicle, four-wheeler or two-wheeler, I need to go for the first service in a month around. Then I need to go for the second service around 3-4 months. Then I am going for the around maybe a year, then maybe 2 years. And after that, what is happening actually? After that, as free service is over, we are not going with the regular maintenance or the regular service sometime. Okay, there are some persons which are again following that scheduled part, but still many of us are not bothered about it. We are using it, and whenever there is a breakdown, then we are going to the mechanic and asking for the maintenance activity. So basically, why we are not going after the free service period? Because we don't want to pay extra money. We are having this confidence that, okay, my engine oil is good, I need not to replace it because I have not run that vehicle. So those kind of costs which are not required, because I personally feel that I have not used that much, I have not traveled that much, so that engine oil is deteriorated. But still the company will say that, okay, since 6 months is over or a year is over, you need to replace that. So that kind of problem is always there. So again, the cost of replacement of some compulsory part or component, even though they are in good condition, that is pinching me, that is creating pain to me in terms of cost. So I need to avoid such kind of situation. So in that case, third maintenance activity or third technique strategy is coming as known as predictive maintenance. So before going to predictive maintenance, let us look at the preventive maintenance. There is a way through which we are scheduling the activity. For example, here you can see that I am having a bathtub curve in which you can see the number of failure with respect to the time spent by that particular product, component, or any service. So initially when we talk about, initially number of failures will be more, Then there is a normal life in which a number of failures are stagnant somehow. After a certain life is over, components are worn out, and again I need to replace them. So again curve is having more number of failure. So the mean time between failure or mean time to failure is going to be the criteria which is going to indicate that I need to go for the servicing in how much time. So that period between the two service is defined by the mean time to failure or mean time between failure. So that is going to be the strategy in case of preventive maintenance. Next comes predictive maintenance. So when we talk about the predictive maintenance, it is also known as condition-based maintenance. So as I was pointing out, in case of preventive maintenance, there is a problem that even though components are good, we are replacing them. Even though my engine oil can work for another 10,000 or 5,000 kilometers, still I need to change it because time is over. So those kind of activities I don't want. So for that purpose, I am going with the predictive maintenance activity, which is continuously going to monitor all my component activity of that machine, and it is going to go with the scheduling that maintenance task based on the requirement. It is not that you are going to see just, okay, scheduled maintenance is coming in next month and I need to do. No, you are continuously observing the condition of the machine, and based on the condition of the machine, you are taking that decision, okay, I need to go with the maintenance task after 2 days, 5 days, 15 days. Based on the life of the component, you can decide it. So another important that in this particular, you need to predict remaining useful life of the component, that after service of 15 days, 15 months, 15 years, whatever it is, now what is the remaining useful life of that component, and based on that component I am going to decide that when I can schedule the maintenance activity. It may happen that sometimes the condition is giving me indication that, okay, within a week this particular gear component is going to fail, so I am going to conduct my maintenance activity based on that remaining useful life. So in all, predictive maintenance program is having so many advantages. Some of them are listed here. The reduced unplanned downtime at risk. Since we are monitoring condition of the machine in a continuous way, real time, then we are going to have an unplanned or catastrophic failure will be less. So that risk is minimized. Second is reduced maintenance cost. So in this case, again, components inventory I need to keep low, because I know that which component is having how much life, and accordingly I can order it in proper way so that there will be a less inventory in my stock. Then again, overall utilization of assets are maximum, because I am not changing on a fixed time interval. I am changing them based on their condition. So asset utilization is improved. Asset life is correspondingly again extended. Then increased production output. Since overall downtime is reduced, overall production is going to be increased. Similarly, I can also control that when to schedule my maintenance based on the conditions, so that based on my order in hand, I can plan that activity. So overall, these can be the 5 possible advantages. These are the key benefits we can add upon it based on the different application and the industries. Now, when we talk about the predictive maintenance or condition monitoring method, we are having so many methods. Now, none of the methods I can say that it is universal in every application. As we know that nothing is universal for every application. So here also the same thing is applying, that when we talk about the bearing, gear, or whatever component is going to define, that application is going to define what kind of condition monitoring method is going to be best suitable. So some of the techniques are vibration monitoring, temperature monitoring, acoustic emission, shock pulse method, sound pressure, stator current, oil monitoring, field signature mapping, etc., etc. So based on the application, for example, vibration monitoring is very good in mechanical component, temperature monitoring, or we can say infrared thermography can be useful in electronic component. Acoustic emission is also very good technique for the mechanical component and for detection of incipient fault. Likewise, like field signature mapping is good for some application in which pipes and other things are there, so small cracks is going to affect your field signature, and that can be giving indication about the failure. So these are the various techniques available. Some of them let me discuss in bit detail. So one important is oil monitoring. For example, in automobile, we are going with the conditions where we are continuously observing that what is the condition of lubricant. We are taking out some oil from the gearbox, and based on the condition of oil, based on the particles in that oil, we will be able to say that, okay, what can be the possible condition of the gear, whether our oil is having those particles. If yes, then there is a problem either with the gears or the supporting shaft or maybe bearing. So there can be a different categories of methods which can use for the lubricant oil analysis. One of them is chip detector. So filters or magnetic plugs are designed to retain chips and other debris in circulating lubricant system, and these are analyzed for quantity, type, shape, size, and so on. So these are going to be the particle which we will observe, and based on the shape, size, we will be able to tell the condition of the wear of that particular component. Next is the SOAP, that is spectrographic oil analysis procedure. Here, the lubricant is sampled at regular interval continuously and subjected to this chemical analysis known as spectrographic. So in this analysis, we are going to trace various kind of material coming through the wear of different component. Now, whether it is coming from the bearing, whether it is coming from the gears, that we will be able to detect through these analysis of materials. Then another technique is infrared thermography. Thermography is a very useful condition monitoring technique based on the emission of infrared. So as everybody is knowing that whatever is there in the world, they are having certain temperature which is above absolute zero temperature. So whenever there is a temperature above absolute zero, then we are going to emit certain radiation. So that energy or the radiation emitted by objects or machines, we are going to check the pattern in those machines, and that is going to indicate what is the problem with our machine. So you might have seen different thermographic camera like this. We can have cameras which are taking the thermal profile of a machine. So here there is a machine and we are capturing that image, and you can see here there are certain red zone which are hot zone. Here also you can see, and there are certain zone which are coming in the purple zone or green zone. So you can see that temperature profile. Purple zone is having minimum temperature, or black zone is having minimum temperature of 10.6 around, then purple is 15 degrees, then blue is 20 or 25 around, then green is around 30, and red is going around 45. So based on that temperature profile, I can detect that what is the condition. Now, we need to understand that color is not going to indicate there is a problem. I may have a condition already which is in high temperature zone. There may be certain friction, there may be certain problem in that particular component. Because of that, already temperature is high. I need to continuously check for the change in pattern. Remember that whatever condition monitoring technique or predictive maintenance technique we are using, it will be based on the condition that this is the baseline data when things were healthy, and the comparison is always done on the healthy data. So from healthy, how we are going to go in another zone. So I can see that, okay, this zone now, instead of 45, now next temperature may be going 55. So instead, even at present also it is red, but the severity or the change in temperature will be continuously observed, and that is going to indicate that, okay, this particular component is having problem. So this is very effective technique, and infrared thermography is very useful if I talk about the electronic component, because in mechanical components you may be seeing that there is a lot of vibration. I can measure them. But if I talk about the MCB is the electronic component which we usually use in our circuits, but there is a lot of problem regarding that how to check that condition of that MCB. So I know that current is always related with some heat. So I can check the thermographic pattern of that MCB, and that is going to indicate me that, okay, yes, everything is okay with that MCB, or there is some short circuit and there is heat generated, and I can replace that MCB in a timely fashion. So electronic component is judged using the thermography for the condition monitoring part. So these are some of the cameras which we can use for capturing the image, and that can be directly connected to our data acquisition system laptop, where it will be compared with the base signal for the condition monitoring part. Next is the vibration analysis. So mechanical component, when we talk about machine component, when we talk about vibration analysis, is very, very good technique, because we know vibration is basically related with the two things. One is the characteristic, that is known as stiffness. Another is characteristic, that is known as mass. So stiffness and mass, two are the important properties which are going to change the frequency of any system. So if I can observe those kind of change or shift in the frequencies of vibration signature, I will be able to locate what kind of fault possibly that particular component may be having. So mechanical signature analysis or vibration signature analysis is important technique which is used for the condition monitoring purpose. Now, if I compare it with the other machines for other condition monitoring method, like our lubricant analysis, you might have seen that lubricant analysis is taking the chips. We are doing soap analysis to get that, okay, what is the particle size, what is the kind of material. But suppose two component, I'm having two gears made up of same material, or they are installed in the same gearbox. Now that chip which is coming, that is corresponding to which particular gear, that I don't know. So that kind of problem is existing in the lubricant analysis, and in those cases vibration analysis can be very useful, because in vibration analysis each component, even though they are made of same material, but their mass property will be different, their stiffness is going to be different. So that is going to be indicated by their frequency component, vibration frequency component. So I can observe those frequency component, and in change in those frequency component can be used to indicate that, okay, this particular component is having a problem. So let us see what can be the possible sources of vibration in machines. So in general, when we talk about the machine vibration, there are 5 major reasons: unbalance, misalignment, looseness. Sometimes there may be a looseness in your system that you can tighten up, and that is going to reduce vibration. Then bearings and gears. So these are the important things which are contributing some way regarding the vibration in the machine. I hope it is clear till now. Any problem? Yes? Any doubts?
Any questions from participants? Sir?
Yeah.
Any questions from participants? Sir, it is fine, sir.
All right. Yes, so, sir, with this background, let us see that how this unbalance and these misalignment is going to affect our system. So here you can see what is unbalanced. Let us understand that we are having a shaft which is supported on the two support, left hand side and right hand side. We are having two supports which are basically supported by bearings. So we are having bearing support, and this shaft, this system is supported by these bearing. Now we need to understand what we understand with this particular condition of unbalance. So there are two terms. One is the geometric center. Geometric center is basically a center of this geometry. So we are having this disc which is having geometric center at this location. Now second is known as center of gravity. There is a condition where, or the point where whole mass can be assumed as a concentrated. So this is the center of gravity at present. So if my mass is uniformly distributed and distributed over the component, then we will say that center of gravity is lie on this point. So our center of gravity and geometric center both are going to coincide with each other. This is the condition is known as balanced condition. There is no issue. Okay, but when there is a condition where geometric center and center of geometry are misaligned, they are having certain eccentricity, you can see that distance between the two is over here. So if that condition is there, that means mass is not mass center is not coming on the geometric center, this is the condition corresponding to the unbalance. And whenever there is an unbalance, there is a vibration. Why it is going to be there, we'll discuss that. But for understanding of unbalancing, let us try to understand that whenever there is a change in this one, in any of the side, I have taken it as a diagonal, it can be towards x-axis, it can be towards y-axis, whatever it may be, but center of gravity and geometric centers are not coinciding with each other. So this is the condition of unbalance. So if you might have gone through the balancing of your wheels or the vehicles, you are going in the market and you are getting balance, you might have seen that they are checking it for unbalance, and accordingly they are placing certain mass on the periphery. Okay, so what they actually do, for example, in this case, I may have seen these are the two masses which are indicating that there is going to be a mass or unbalance coming in this direction. So what I can do, based on the condition, I'm going to identify that, okay, line of action of this mass may be somewhere here, maybe somewhere here. So based on that, I will be placing a counter mass over here or at this location. So I will be judging that condition, that location, I can place a counter mass over here, which is going to balance this particular unbalance. Now, in that case, by using these masses at the periphery, I will be able to relocate my center of mass on the center of geometry. And again, I will get the condition of balance of this disk. So this is very important. Now, let us understand that how we do it in the lathe machine. So you can see here that lathe machine, we can have a screw, we can have an additional mass over here to balance it. So that can also be done. To understand it more clearly, that how it is going to contribute in the vibration, you can see there is a video here and a shaft is continuously moving. I am observing it into this plane where axis is perpendicular to this plane. So you can see that when there is a condition of balance, it is continuously rotating in this plane and there is no problem. But if there is a condition of unbalance, in here you can see there is a red spot which is indicating there is an unbalance and the mass is going to have force in this direction. So shaft is going to have force in this particular direction. So in that kind of condition, I will be having extra force acting in that particular direction where this red dot indicating the unbalance, you can see that it is going to move that particular shaft in that direction. So you can see it is making an orbit kind of structure continuously moving. Right? Now you can see that how we can check the unbalance. So to check the unbalance, let me have a simple experiment. You can see here, if I indicate, I can have a dial indicator attached to the shaft and you can see that how this plunger is moving with respect to the shaft. So when this mass is moving this whole shaft towards the left, the indicator is going in the +10 direction or minus and in opposite direction when it is going towards the right hand side. So you can see that plunger is pressed, plunger is expanded and continuously the dial is indicating from -10 to +10, -10 to +10. So kind of oscillation I can see in this indicator. So basically oscillation is indicating that there is a kind of vibration somewhere. So if now I connect this plunger with the indicator, now I am having a paper which is continuously moving on the right hand side and this plunger is drawing. So you can see that -10 to 10, how it is drawing on the paper. So you can see here I am having a periodic wave, a harmonic wave you can observe in this signal, which is having a certain frequency based on the time period between the two. I can observe that time and divided by 1, but 1 divided by the time is going to give me required frequency of oscillation. So you can see that this is going to be the indication of vibration. So unbalance is indicating that there is a vibration. It is going to be the cause of vibration in the machine. Now, what will be the frequency of this vibration? So you can see that frequency of plunger going compressed and expanded is dependent upon the rotation of this shaft. So in a single rotation, it is going to have that plunger is pressed, then expanded, then pressed, then expanded. So it is going to indicate the time period of the oscillation. So whenever we will be having an unbalance, that time period of oscillation will be corresponding to the rotational frequency of the shaft. So if I take the, rather than this time response, if I take the frequency component of this is going to give me the component which is going to be the corresponding to the shaft rotational frequency, right? So this is example. Now in the same example, suppose if my unbalance is increased, I am having more unbalance, or if I am having less unbalance, what is going to be effect of that? So if I am having more unbalance, what is expected? That because of that higher unbalance or the more unbalance in the system, I will be getting what? I will be getting more displacement. So in that case, the amplitude, if I again look at this condition, if unbalance will be more, it is going to move this shaft over this axis by a larger amount. So that is going to indicate that by the amplitude will be increased. But when we will be having higher speed, there are two things. One is the amplitude will be defined by the amount of unbalance. Second is there may be a condition in which we will be having higher speed. So if I will be having higher speed or lower speed, here you can see that this is the higher speed. So when I am having higher speed, because of the higher speed, now time period is less, or time period when it is a low speed, it is going to have a more speed. So I may be having change in amplitude, I may be having the change in the time period. So amplitude will be affected by amount of unbalance, and speed is going to affect my frequency of oscillation. So these are the two important components for the vibration analysis, amplitude and the frequency, which are going to give me idea about whether there is a more unbalance, whether it's less imbalance, whether speed is high. So those are the parameters which I can check using this vibration measurement. And you can see here that graph I am getting, that is known as time response, because it is coming with respect to time. Time is moving, and with respect to time, I am getting the amplitude. So this kind of response is known as time response of the system. Now, second important reason is misalignment. Now, misalignment can further classified into the two categories: parallel misalignment and angular misalignment. So whenever there is a misalignment in which shafts are parallel to each other, there is an offset between the shaft, that kind of misalignment is known as parallel misalignment. Second category is angular misalignment, when shafts are having some angular displacement between them. There is an angle between them. So these two kind of misalignment are also reason of vibration in the mechanical system. So parallel misalignment is basically coming when we are not installing them in a proper way and there is a offset between the two shafts. Angular misalignment may be because of some deformation, because of some load, maybe because of thermal parameter. There is some thermal parameter coming, which is giving me this angular dislocation. Initially, it may be aligned, but after a certain time, because of thermal loading stresses, it may have some angular kind of displacement, which is giving this angular misalignment. So this is going to give extra load on the bearing. You can see here that when shaft is moving, on one side it is compressing the one part of the bearing, and second side it is indicating the second part. So continuously extra load is coming on the component, mechanical component, and that is going to result in early failure of these mechanical component. Now how to find out that what component is having failure, what kind of misalignment. So in case of parallel misalignment, you will be observing these vibration peaks at 1x, 2x and 3x, and in general 2x peaks will be dominating that frequency spectra. But when we talk about the angular misalignment, the 1x frequency is going to be appearing in our pattern vibration or the frequency response spectrum, right? So as I was mentioning you earlier, there are two important parameters. One is the amplitude, another is frequency. So whenever there is a problem, you will be observing either change in your frequency or you will be change in your amplitude. So these are going to be the indication of the problem in your system. And by observing that, you can find out whether it is a problem of unbalanced misalignment or parallel misalignment, angular misalignment, bearing, gear, whatever may be the condition. So that will be used to find out the problems in the machine. Now, another sources of vibration is the rolling element bearings. So rolling element bearings, you can see here that it is having three, or we can say four component. One is the inner race, another is outer race, third is the ball. Fourth component is not shown here. Basically that is the cage which is separating these ball by a constant angular displacement. So these are equally spaced because of the cage in between them. So you might have seen actual bearing also, in which you will be seeing all these four major components. So whenever there is a bearing, there is a vibration, because there are two kind of situation. One is parametric excitation. There is another reason is the defect. So parametric excitation may be because of the point contact or the line contact. Whenever there is a bearing, there is maybe you may be using ball, you may be using roller. So ball are having a point contact between the inner race and outer race, that is going to give the stiffness or the restoring force based on the point contact. But when we are having line contact between the roller and bearing, there will be a different kind of restoring force. So that restoring force type is going to change, which is going to give the vibration in the system. Second important component is the radial internal clearance. So there will be always some kind of clearance given in the bearings for compensating thermal expansion due to the higher speed. So that internal clearance is going to be the cause of vibration in the system. Then balance and unbalance, as we have already discussed, this is another reason. So these three are coming in category of parametric excitation because they are parameter dependent. They are going to be there in the system because of the parameter mentioned in these three categories. That is point contact, line contact, maybe clearance, maybe balance and unbalance condition. Another is defect. Now, defect can be categorized into the two parts. One is the localized defect, another is the distributed defect. Localized defect, as name is indicating, it will be located at a certain location in the bearing, a particular location. Okay, so it may be in form of a small crack, it may be in form of pits, spalls, dents or bumps. All these can be at a certain location. Now, that is one type of defect. Another is distributed defect. Distributed defects are there on the complete periphery of the component. So like waviness, because of irregularity in due to the manufacturing operations you might have used, there may be an irregularity. Ball can be off size, so that can be another irregularity. For example, here you can see that there is a spall on the inner race. A particular location of material is removed, so that kind of defect is known as localized defect. In another, you can see that here you are having a defect on the outer race at this location. So material is removed at a certain location. So that kind of defect is known as localized defect. At a particular location it is existing. Second, this is again an example of localized defect. In second category, we are having distributed defect. So you can see that it is definitely an exaggerated figure where I have just enlarged it to an extent that you can see it by the naked eyes, but actually it may be of 10 micron level or 20 micron level based on the kind of machining operations you are doing, finishing operations you are doing. So you will be having complete waviness structure on the inner race or the outer race, or even it can be on the ball also. So ball can also have some kind of irregularity of micron level, and that kind of defect is considered as a distributed defect. You can have some deviation of perfect spherical shape to the elliptical shape, that is again coming in category of the waviness or off-size ball distributed effect in case of bearings. Next important component is gears. That is also causing the vibration. So you can see here that two gears are mashed together, and here they are contacting at this location. So whenever there is a contact, there will be an impulse generated, and that impulse is indicating that energy is coming. So that frequency is going to come in your spectra, and vibrations are going to be generated. Then you can see there will be maybe a defect. So if defect is there, a material is removed, a tooth is removed during operation, there will be no contact between the two tooth, and that is going to again indicating in the your frequency spectra, because amplitude may be decreased or frequency may be shifted. So that is going to be the indication, yes, there is a problem in your gear system. So these are the basically different causes of failure into the bearing or the gear. Now let us talk vibration of bearing in some more detail. So here you can see, as I was talking to you, that there are certain frequency we need to observe continuously to think about or to find out what kind of component or what particular component is having defect. So I was talking about that bearing is also having different component. So outer race, inner race, ball, these are the three important components which may have defect. So based on the kind of defect in the bearing, you may be having outer race defect frequency, inner race defect frequency, or ball spin frequency. So these can be the different defect frequency, and cage rotational frequency is going to be the one of the fundamental frequency, because our balls are rotating with that. So to understand it, formula I am not going to discuss that how it is derived. You can see the literature, you will be able to get it. But for understanding purpose, that why these frequencies are going to be different, even though they are coming from the same component, let us understand with this video. So here you can see, oh, I think there is some problem in video. Okay. Sorry. Video is not playing. Okay. All right. I think there is a problem. So let me explain it with the another diagram. Or now you see again on this bearing part. Now cage is retaining all these balls, and these balls are continuously moving in this outer race, which is considered normally as a stationary component. Inner race, which is shown over here, that is continuously rotating, and with the shaft. So this is the shaft. Inner race is rigidly mounted with this shaft by using press fit. So in general, bearings are press fit on the shaft, so that the speed of the shaft and the speed of this inner race will be same. When this is going to move, it is going to move these balls, and these balls are moved in the cage, and outer race is considered as stationary. So if you remember that, there is a condition which is known as loading condition. If I consider that shaft is having weight in the downward direction, so the condition of load zone will be coming something like this. If you remember that, load zone will be coming downwards in this direction, and it is going to be maximum at this point. So this kind of load conditions will be coming, and because of this load, you can see the balls which are coming in the load zone will be compressed, and that will be participating in the restoring force. But the balls which are going up, they will be having certain clearance between inner and outer race, so they will not be compressed and they are free. So in that condition, because of this balls which are coming in this load zone, that is going to give the vibration in the system. So that vibration is because of the natural restoring force, because of these balls are coming in this particular load zone. So what is the frequency of coming a single ball in the load zone? That will be nothing but the cage rotational frequency, because you can see that balls are retained in the cage and cage is continuously rotating. So a ball is coming in a single rotation with the cage. So cage rotational frequency is going to be your fundamental frequency. And if I consider all balls, it will be NB into omega cage, which is cage rotational frequency. Now let us consider there is a defect. There is a defect over here. It may be in this term, that is, I am indicating that, okay, this is going to be a removed, material is removed like this, a deep cut. So whenever the ball is going to pass through this particular defect, or let me clear it first. Now, okay, now I can have two situations. I can have this kind of dent. I can have this kind of dent in which material is removed from this location. So whenever a ball is going to pass through this outer race defect, which is having a dent over here, it is going to have an impact on this race. So you can see that ball is coming here, it is going to have an impact, and that is going to generate an impulse. So that frequency of impulse is going to indicate that this component is having a problem. Outer race defect is having certain problem. But if this is defect is not in the outer race, if this defect is in inner race, for example, if I consider somewhere here, so like you can see this red dot. So if that red dot is considered as a defect in the outer race, you can see that defect is also rotating. Previously defect was stationary, outer race, but now defect is continuously rotating with the shaft. So the relative velocity between the cage and inner race is going to have that impact between the ball and the inner race defect. So that is going to be indicated by the inner race defect frequency. And third category is going when there is a defect on the ball. You can see here there is a defect on the balls also. On this particular ball there is a red indicator you can see here, and that indicator is basically showing you that yes, there is a problem in this ball. So this is continuously spinning. So you can see that once it is going towards, this defect is going towards the inner race, once it is going towards the outer race. So in a single spin of a ball, it is going to touch twice. Once it is going to touch inner race, once it is going to touch outer race. So ball spin frequency is going to have two impulse. So that is going to define frequency in case of ball race defect. So now let us come back to our frequency. So you can see that we are having cage rotational frequency given by equation 1, which is dependent upon the definitely inner race. D and D are our ball diameter, and we are going to have pitch circle diameter of the ball. Alpha is going to be your angular contact angle. Then outer race defect frequency is going to be defined by NB into this omega cage, which frequency is going to be higher than the cage rotational. Inner race defect frequency is going to be plus sign. So this frequency is much higher than the outer race defect frequency because of this plus sign. For ball bearings, alpha angle is considered as 0. So alpha is the angular contact angle. Now, if I talk about the ball spin frequency, it is going to be given by equation 4. And whenever there is a defect on the ball component, we are going to have that rotational frequency on the 2 into ball spin frequency. That frequency component we are going to see in the vibration spectra. And that is going to indicate, yes, there is a problem in the vibration spectra. Then comes fatigue life. If you see on this figure, we are having different components of the bearing failure. So most important component are lubrication and fatigue. So lubrication and fatigue are the major reasons of failure of these bearing. So let us discuss them. So when we talk about the fatigue, which is of 34% cause, 34% is coming because fatigue is coming because of this continuously load coming on a part and then removal of that load. So whenever we are having extra load because of misalignment, it is known as parastatic load. which is coming as change in that load condition due to the unbalanced condition or the misalignment condition. And you can see that effect. If that load coming, the overall L10 life, that is bearing life, is reduced by 1 upon cube. That is, if load is doubled, it is going to be 8 times. So 8 times 1 upon 8 will be the life of the bearing. And similarly, if you see the change in the speed, if RPM is changed by a certain amount, it is going to again adversely affect. But obviously, it is not that bad as you can see with the load condition. So when we are having a system with the unbalance or misalignment, the life of the bearing is going to be drastically reduced. So you can see here that we are having a condition in which we will be having certain thing in the load zone, and when it is moving through the load zone, we are having this thing, and you can see that when it is moving through the load zone, it is going to have, because of unbalance, there is a red mark. So continuously load is rotating, coming on the outer race once, then second time, then third time, as per the condition. This is going to give the condition of the fatigue. So this is going to reduce the life of the bearing. So when you see the inner race here, you can see that kind of mark you will be observing on the component, which is indication of the fatigue life. Then there is a second condition which is corresponding to the lubrication. Poor lubrication or excessive lubrication condition both can be there, and that is may also cause of the failure of the bearing. So here you can see that we are having a bearing and lubrication between these. This is our outer race, this is the ball, and this side you can see that there will be a thin layer of lubricant between this ball and the outer race, which is basically preventing metal to metal direct contact between the ball material and the outer race material. So on the one side it is connecting with the outer race, similarly it is going with the inner race at the top. So ball is continuously moving like this. Now we will be having a condition where there is a gap. So you can see that lubricant, this yellow lubricant, is having the gap between the inner race or inner race or ball, or I can say if this material on the top is the ball or outer race, there is a gap between the two, and we are in safe zone. There is no problem. And irregularities on this surface, you can see these are indicating that irregularities of micron level due to the manufacturing process. So when there is a lubrication, there is no metal to metal contact. But if this lubricant is removed or it is inadequate, in that case directly there will be a metal to metal contact and there will be a lot of wear and tear. So that is going to harm your bearing. So in that case, this kind of mark you can observe. So you can see the difference between the marks due to the poor lubrication and the marks we have seen for the fatigue life. So that kind of difference is able to tell us that what kind of problem may be there in your system. Then next is contamination. Contamination is again contributing around 14% for the bearing failure. So it may be because of the particles are coming due to the oxidation, or maybe caused due to the lubrication shortage, machine wash down, location and all. So in this case you can see here there are, suppose moisture is there, so there can be a particular reactions with the surface and you can have those kind of marks. You can see that because of a low bearing was not running and because of the some contamination, you can see there are marks on the bearing surface. So these kind of harsh environment can be there, which are indicating that okay, there may be a chances these outside foreign particles are coming between the surfaces. And when these particles are coming and they are not very hard or very soft, you can see that ball is passing to them, but because of the passing ball they are compressed, so extra load is coming, impulse is coming in your system. But when these particles are of different nature, it may be very soft, it may be very hard. So based on the kind of particle, if it is having a hard surface, then the surface of the outer race, this is going to make a dent in, or it may be the reason of pitting in the surface. When, like in this case, you can see that now hard particle is removing material from the surface and it is going to remove continuously this material, and it is material is removed from the outer race. So this kind of problem may be there because of the contamination. In second case, you can see the material is soft. Contamination is done by a material which is very soft. So it is going to be flattened in the process, but it may create an extra bump over here. So that is going to be again an indication that yeah, there is a problem in your bearing. Next is the handling and installation. So that is again a cause of, so you can have a bearing which is not properly aligned, a cog. So you can see that perfect bearing is like this, but if out you might have seen that here again you look at this, that inner race is not properly aligned with the outer, this kind of condition cog bearing. So we are having misaligned condition. So in this particular case, because of the poor installation, poor handling of this bearing, we are having a situation of extra load, and the overall fatigue will be happening on the bearing, and the life is reduced, as I discussed earlier. Here you can see that poor installation, loose end, all these are also cause of failure of the bearing. This is going to have vibration of overall components likewise. Now, after understanding this, what we understood that condition monitoring or condition-based maintenance is very, very important for finding out condition of our machine, which may be good for scheduling the maintenance activity. Now, remember that condition-based maintenance, when we talk about, we are talking about the real-time monitoring. Real-time monitoring, when we talk about, it is consisting of three important aspects. One is the modeling of the system, then second data acquisition, then fault classification methodology. As you might have observed that I was talking about some mathematical formulation, I was talking about some characteristic frequencies. So first task to do real-time condition monitoring is we need to understand that what particular component is giving what characteristic frequency. So gear is having their own characteristic frequency, bearing is having their own characteristic frequencies, which we have already defined by 4 equations. So basically these mathematical models, these equations are telling us that what can be the possible cause of vibration and what can be the possible frequencies of those vibrations. So we need to understand through the modeling that what will be the possible frequencies and corresponding pattern of vibration spectra. So that will be very useful. So first task is to model our system to understand these characteristic frequencies. Second is to acquire data. Whatever modeling we are doing, we need to validate our modeling part. We need to validate our results. So that we need to do. So for that, we need to have an experimental setup through which we can acquire data, and that acquired data is used for the validation of the models. If something is missing, it is not close to your actual system, you need to see your assumptions, you need to see what realistic model or component parts variables you can consider. So that is going to improve your model. Then again, these acquired data can also be used for the fault classification purpose. So you can use models also for the identification of characteristic frequency, and you can identify the faults, or you can see those data, you can see the frequency spectra and check whether the characteristic frequencies are corresponding to the gear or the bearing or the shaft or unbalance or the misalignment. That is going to indicate that yes, there is a problem in your system. So this is about that. These are the important aspects of the real-time fault diagnosis system. So if I talk about the bearing, in this particular study, what we did, we have considered that contact between the ball and inner race and outer race. Inner race and outer race is considered as a spring mass damper system, this contact. So we have considered stiffness, we have considered damping over here, and they were used to model this particular system. So using Hudson theory of elastic contact, that is the nonlinear contact theory, we have developed equation of motion which are given by the 7th equation. You can see that Hudson contact force is nonlinearly related with this r theta I, where r theta is the radial displacement of the ith ball, k is your stiffness. So we are going to have this nonlinear force which is giving this restoring force. So considering that, I am calculating a radial displacement of the ith ball which is given by this equation. So x and y are displacement of the bearing. Because of that, radial direction displacement will be x cos theta plus y sin theta. minus gamma plus delta I. These two important parameters I am taking, gamma and delta I. Gamma is considering because of clearance, because whenever there is a radial displacement, first it is going to compensate that clearance, then only there will be a contact between the races and the ball. Delta I is going to be the corresponding to the defect. If we are having a defect in the bearing, it is going to be considered. If it is not there, then it is going to be 0. So using that, I am getting the F theta I, which is the radial force coming on the bearing, is given by equation 9, which is the nonlinear force. And if I take the component in x and y direction of this radial force, which is given by equation 10 in x and y direction, which can be used to derive the equation of motion, which are given over here by equation 12. So I am going to get equation of motion for as a 2 degree of freedom system. You can see here we are having equation for x direction and y direction forces. We are equating them by the Newton's law, or you can use the D'Alembert principle or any other methods of getting these equation of motion. So nonlinearity is coming in the system because of this nonlinear part of this stiffness of this restoring force, and this is going to be because of damping as well. Damping force is also defined in this particular work by the nonlinear equation 11. Here we have used these equation and we have considered these parameters for our study: speed of rotor, radial clearance, balance and unbalanced rotor effect, and defect condition. So when we have solved these equations using the different Newton-Raphson method in MATLAB programming, we did it and we were getting the different responses. So you can see that we have considered the defect on the outer race, we have considered defect on the inner race, we have considered defect on the ball component also. So as I discuss all these frequency to you, so I am skipping all these parts, but I am directly coming to the responses I have obtained. So you can see this is the response plot for the outer race defect. So here you can see that I am getting clear peak on the outer race defect frequency known as ball process frequency of the outer race, omega BP. So you can see there is a clear cut peak coming over here in horizontal as well as vertical response both. Right now, in second condition, I'm getting the interaction between the ball passes and cage frequency with the outer race defect. So now pattern is changed, and pattern you can see that here I'm getting more and more peaks over here. So it is basically going towards the chaotic regime. That is, instability in system is coming because of this outer race defect at the speed of 4805. In the previous 2000 RPM, I was getting clear peak and the response was periodic in nature. The figure on the downside, basically these are frequency response, and the top side, these are known as our Poincare maps, which are indication of the different nature of the response, maybe periodic, quasi-periodic or chaotic. So here you can see that outer race defect, which is coming corresponding to the, here omega BP is coming subharmonic of that, and omega cage frequency coming in the frequency spectra, and I'm getting a lot of chaotic vibration in the system, and amplitude is drastically increased. So if you can see here, the amplitude was coming around 2 micron here, and here it is raised up to a 4. So around double we are getting is the amplitude. This is the corresponding to the different speed. You can see a outer race defect. Again, pattern is continuously changing. Here you can see that we are having a quasi-periodic kind of response. This is again a periodic with the outer race defect at the higher speed. Then same kind of analysis is done at different speed, and I was able to get this kind of response plot, which is indicating two zones of instability, A to A dash and B to B dash. These are used for avoiding the condition of instability in the system, and system should be run at the stable zone. So I should better, whenever we are having outer race defect, I should be better operated in this between A dash to B regime, where there is a less amplitude of vibration and stability of the system is there. So with the inner race defect, again same kind of analysis was done, and you can see there are 3 unstable zone I was able to get it, and the peak amplitude is coming whenever there is a chaos in the system. For the ball defect, again 3 responses were 3 unstable zones are appearing like this, and these are used for identification of high amplitude the response. So you see that basically what I am observing in these responses, I am observing characteristic frequencies corresponding to outer raised effect, inner raised effect, or the Bald effect. I am also observing what is the peak to peak amplitude. So amplitude and frequency, two important components I need to continuously observe to find out the condition of the machine, and that will be useful for my identification of operating conditions based on the defect in the system. Then another method I have used, and it was published in ASME journal, which was based on the response surface method. Response surface method is used by many of the mechanical and production engineers for identification of combined effect. In general, what we do, we are studying our particular parameters. One parameter we are changing, and other parameters we are keeping constant, and we are observing that what is the effect of that change. But when we talk about the combined effect, we are saying that response surface method is considering the combined effect of multiple parameters. So in this particular analysis, we have considered different parameters, that is defect size of inner race or outer race, if they exist simultaneously also. So using that, I have considered these parameter: outer race fault, inner race fault, ball fault, and speed of the rotor. And these conditions I have considered, and these kind of response surfaces I was able to obtain. Here you can see that interaction of outer race and ball defect in this figure B. Here you can say inner race and outer race defect both are interacting together, and here you can see in the third C diagram, ball defect and inner race defect both are interacting with each other. So the value of inner race defect I have varied from 0 to 2, and for outer race I have varied from 0 to 3. For the ball defect, I am varying it from 0 to 4. So these are the different size of the fault I have considered, and using that I have generated these response surfaces for the analysis purpose. So this study was having one important concept. Here you can see that surprisingly, when we are having higher value of ball defect and outer race defect, I was getting less amplitude. The vibration amplitude with the outer race defect was increasing, with the ball defect was increasing, but when both were existing, it was going down. That was a unique thing. I could figure it out in this particular study. So that was happening because of the a special effect known as self-pinning effect, which is basically amplitude is decreasing because of continuously ball is making those surface as a pinning operation we do in the mechanical, and that pinning operation is reducing the amplitude of vibration from the system. So these are the references I have used. So now house is open for the queries. I'm having a good time, so let us discuss more in this query session. If you have any doubt, you can ask.
Any questions from participants? Any questions from participants? Subodh?
Sir, there's one question from the Google Meet chat by Dr. Rajesh Joshi.
Yeah. Please.
Sir, he states that most of the people do not prefer AMC for domestic equipment due to cost involved.
Right.
Even though they are ready to pay higher amount at the time of component failure, don't you think that there is a lack of awareness among the users, or they don't have faith in service providers?
The comment is very valid in terms of Indian scenario specifically I talk about. Then in Indian scenario, we are usually go with the breakdown maintenance still. We are not believing on the predictive or even preventive. Till we are having free service, we are going with the our vendor or the particular agency, and we are getting our service done. But after that free service period, we don't want to pay extra because we think that it is unnecessary. Okay. Now, there are two things. That first of all, there may be components which are not that severe. Okay, it may be like for a fan, you may be having fan in your house, and you are not bothered about, okay, if suppose I need to have some problem in my fan, I can get it changed whenever there is a problem. Okay, but there are certain applications there you cannot make any compromise with these conditions. You can do it with the domestic equipment, definitely you can do it. But when we talk about the plants where your whole production line is going to be affected, so you may be thinking of, okay, I will not go with the AMC because you are not bothered about, okay, this is going to be a huge cost or the loss. Suppose you are having a domestic equipment, your washing machine. So if it is stopped, fine. You may be waiting for a day or two, no issue. You can get it done. But if I talk about a production line, if there is a delay of a day or two, it is huge damage to your system. Like you can see in COVID situation, if I am not getting my inventory, what is going to happen? It is very challenging. So what I need to do, I need to continuously observe those changes in my things, and I can fix that. Okay, these are the control boundaries or the warning signals. I can identify that and I can use it for the prediction of failure. Similarly, if I am having another application, for example, in which humans are involved, maybe railways, maybe your aviation industry. Can I tolerate that kind of situation in aviation industries? Okay, let the engine fail first, then I will get it repaired. No, in that case, I am having a lot of sensors installed. They are continuously giving me a lot of data. That's why we need big data analytics nowadays, because a lot of data is coming through the sensors and I need to analyze those data in real time and I need to predict that failure condition. So I cannot tolerate in those conditions that, okay, let the failure come. So again, overall objective is to reduce the cost. Now, maintenance cost, when we talk about, it will be involving the cost of the service person, cost of the overtime, it will be involving cost of the component, it will be involving the cost of the inventory. So in all, if this cost is minimized, that is your objective. If you feel that, okay, I can wait for another month, another day, another 2 day or 5 year, fine, you can go with the breakdown maintenance. But if your application is such that you are going to have more losses because of the downtime, you are going to definitely go with this kind of maintenance activity, which is reliability based maintenance, or we can say condition based maintenance. Anyone else?
Sir,
Thank you, sir.
sir, another question is from Mr. Amit Kumar Kundu. He asked us how to define time for scraping of equipment from maintenance point of view, and are there any specific tools to define that?
Actually, when we talk about this particular question, let me go back to our maintenance strategy slide. In this maintenance strategy, if you look at this one, this is important. You need to understand every mechanical component, electronic component, every product is having certain life. Even if it is your idea or service, that is again having a certain life. You cannot use that your idea for infinite time. Our idea is unique or it is sellable up to a certain life. So we are having this bathtub curve, which is going to define this particular period. So you need to identify what is going to be the time between failure. So obviously initially time failure will be very high. Then after a certain life, it is going to be the normal life. Then again wear and tear will be there. So for your particular application or the product, you need to see that, okay, now this is the time, again rate of failure is continuously increasing and it is giving me more and more cost. So for example, when we purchase a car, normally nowadays there is a tendency that if you want to change your car, you are changing it after in between 5 to 7 years. Why? Because after that, no funding agency is going to give loan to anybody else who is purchasing your car. Second thing, after 5 or 7 years, it is going to have more maintenance requirement. So rather than going with that more maintenance thing, I am going to change it so that new vehicle will not be requiring that particular maintenance task done. So these kind of decisions as a company, as an individual, you need to take based on the mean time between failure or mean time to failure. And that, okay, when this activity is continuously occurring, then you need to change your system. Whole system need to be replaced.
Thank you,
Good afternoon, sir.
Good
Good afternoon, sir.
Good afternoon.
Good afternoon, sir. Can I speak, sir?
Sure.
Sir, in a condition monitoring system, the vibration and noise are very closely associated with each other. So,
Right.
in terms of to know the condition of the machine, the noise meters can enhance as one of the tool. So, how far it is reliable for know the reliability of the machine in terms of breakdown or some other vibration leads? How far?
Am I understanding it correctly? Let me just explain. You want to ask that whether noise-based condition mounting is good or vibration mounting is good, or your question is something different. I couldn't get it clearly.
Yes, actually, sir, the vibration noise are closely associated because the noise is a measurement of vibration. Is maybe I may be correct or not? I don't know.
Okay.
Sir, you are the expert. You
No. You see that whenever we talk about the academics or the research, we all are the learner. Okay, we learn from each other. Nobody is perfect, and when we understand that okay, I'm perfect, we stop learning. So I don't consider myself as expert. I am just sharing what I did. And based on the experience, we are going to learn from you also and different conditions. So there is nothing like expert. So let us discuss rather than give you expert opinion. So in my particular view, noise and vibrations are definitely closely related, but there is still difference. When we talk about the vibration is going to indicate particular failure, but noise can come from the different sources. Okay, so the outside surrounding is also going to be affecting this noise environment, a small noise disturbance. So whenever we are doing kind of noise analysis, I need to go with the special design chamber in which other effects can be negligible. Okay, so in general, that's why when we talk about the machine condition monitoring, we are going mainly with the vibration analysis. But still, I feel noise and acoustic, both techniques are also very useful and able to get the idea about the incipient fault, because there will be definitely change in that pattern also. But they will be suppressed by other signals associated with the adjoining machines or some other noises in the environment. So to isolate them, that is becoming a challenging task. Same with the vibration, but in vibration, it is possible because we can place that sensor on the location where you will be having dominating vibration at a particular frequency, and even those frequency filters can also be used for filtering out other components.
Yes, sir. Thanks. Right? That means the noise is maybe the not a reliable one will compare to vibration analysis. As you said.
No, I'm saying, remember that we cannot rely on a single part. Okay, when I have studied that acoustic emission is better technique for determining incipient faults. Okay, yes, but in acoustic emission, basically we are talking about the metal contacts and waves are coming in as a stress waves or strain waves. Then we are going to observe those changes in those waves, and we will be able to see that okay, there is a crack inside the material, okay, or there is cavity inside the material. So those can also be observed from that. But again, those techniques can be costly in terms. Even sometimes, recently I have studied that vibration sensors or the acoustic sensors, again, they are having another that they are having a larger size or the weight is more. So when you are placing them, nowadays you can see every machine is becoming so compact. So in those compact machines, installation of these sensors can also be a tedious job. So rather than doing the analysis using vibration and acoustic, I am using somehow some kind of motor current signature analysis, which is going to give me indication. So techniques and signal processing are being developed, methods are being developed, so that the combination of these techniques can give you best possible result with the constraints given to you.
Yes, sir. Thank you, sir. Thank you very much, sir. Thank you, sir.
Okay.
No, sir, not yet. Any questions?
So you can ask questions from your side.
Sir, one is there that which is the best bearing fault detection technique?
I think I have already given that answer that we cannot say that this whether current signature is best, whether the vibration is best or the acoustic. It depends upon the constraints you are having. Okay. Now noise is again a good technique, but you need to have a iconic chamber where you will be suppressing all other noises. So in industry, vibration is considered as a most popular technique, I must say, because it is giving quick assessment of the condition, and it is requiring certain filter which can explicitly suppress other signals coming from the other machines or the components. Yes.
No, sir, it's the same one, that apart from RSM, any other tool like ANN that can be used.
No, let us understand that when I was talking about the bearing fault diagnosis, real-time fault diagnosis, I was talking about the modeling fault classification methodology. So RSM was used just to see that what is going to be the effect of different parameters. So the purpose of using RSM was totally different. I can definitely use fault classification. I can use AI techniques there. I can use neural network. I can use support vector machine. I can use transfer learning. I can use deep learning. All these methods are nowadays very popular for the classification of the faults. And those methods can again be selected based on the particular component you are understanding or the data you are having. Sometimes like support vector machine, you can work with the small data set. That is again good thing. If I want to have a features which are automatically being calculated, then I can use the transfer learning method. If I want to use any deep learning network in which you will be having more hidden neural layers, that can also be done. So fault classification methodology, if I am doing it using the feature based condition monitoring, that is going to be entirely different session. If some time will permit, I will take that lecture also, and based on your organizers, and I request your head of the department, Powal sir, also. So whenever he will be having time, and we can have another session completely on the AI techniques and their application for the fault classification. So that can be done, but these techniques are there.
Okay, sir. Is there any question? Okay, sir. So Professor Ganay, can we conclude now? Professor Ganay, can we conclude now? Okay, sir. So,
Okay, sir.
thank you, sir. Dr. Pawan Kumar Kake, sir, thank you very much for accepting our invitation. And it was a very informative and excellent session. You explained very well about the maintenance strategies, condition monitoring, sources of vibration in machines, and bearing fault diagnosis. Thank you very much, sir.
Thank you. Thank you, everyone. Thank you
Okay.
Thank you, sir.
for listening.
Thank you very much, sir.
Okay, good day.
अभी हम आपसे बात कर रहे थे सर, तो कंक्लूड किया अभी. हाँ जी जी हाँ सर, बोलिए सर. यस. अच्छा 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 अच्छा. ओके ओके ओके, ठीक ठीक. सो आई हैव टू गो टू यूट्यूब ना. नहीं नहीं, आई सॉ योर मैसेज, यू पोस्टेड मैसेज ना. ओके 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 ओके. आई हैव टू. ओके 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 ओके. हेलो, हाँ सर, नमस्कार सर.
अच्छा अच्छा, सॉरी सॉरी सॉरी, हाँ हाँ हाँ, अब हो गया ओके, आर्यन ओके ओके बस। Hello all, I welcome you all for this presentation. Hello, am I audible? Okay, so I welcome you all for this presentation. My name is Dr. Girish Verma, and I will be presenting aspect of modeling aspect of ultrasonic assisted milling process. So let me just share my slide.
Dr.
Yes,
Girish Verma,
yes,
just
yes,
a
yes.
moment, please.
Yes.
Subodh, are you there?
Yes, sir. Yes, sir.
Okay, you start now.
A very good afternoon to everyone present here. Dear participants, today no feedback forms will be sent as some participants are not being able to fill the feedback form through the WhatsApp group. So we request you to please join all the sessions either through Google Meet or through our YouTube link, and attendance would be taken directly through these platforms. This session is on the topic Modeling of Ultrasonic Assisted Milling Process. We have with us Dr. Girish Chandra Verma. Sir, you are an assistant professor at IIT Indore. You received your PhD and MTech from Indian Institute of Technology, Delhi. You have published a number of journal papers in reputed international journals. You were involved in an India-UK project on modeling of ultrasonic assisted manufacturing processes. You have also received the prestigious Gandhian Young Technological Innovation Award. I request you to please start with the presentation.
Thank you, Ms. Dividi. So I will start my presentation. I welcome you all for this session. Now I will present a brief aspect of ultrasonic assisted, modeling aspect of ultrasonic assisted milling process. Now, okay. Yeah. I'm just sharing. Yes. Now, can everybody see my slides? Okay. Okay. So I will present a brief about this modeling process. I cannot explain the complete phenomena which goes behind this process because it's a very tedious thing. However, I will try to summarize all these things in such a way that you will be able to understand the basic mechanism, how to model these complex processes. So before going into this presentation, I will brief you about the contents which I am going to deal through this presentation. First, I will try to explain the basics of ultrasonic assisted milling process. What is the physical phenomena that goes behind this process and how it is different from the conventional milling operation. Then I will give a slight information about how to develop a model and what are the different aspects of model. Okay. Then I will discuss about the model development of ultrasonic assisted machining process. It's basically a review kind of thing, a general aspect which is followed by most of the researchers in the prior work. Now, see, ultrasonic assisted machining process is a superset of ultrasonic assisted milling process. Ultrasonic assisted machining process consists of ultrasonic assisted milling, ultrasonic assisted drilling, so on and so forth. These are the processes which comes in this domain. I'm just going to deal with this ultrasonic assisted milling process. Then after this explanation of how to develop these models, then I will explain how to validate the models and what are the things that we should consider while validating any particular mathematical model. Now, coming on to the basics of ultrasonic assisted milling process. Now, ultrasonic assisted milling process is a conventional milling operation performed with the assistance of ultrasonic vibration. What it means is we are in conventional milling operation, the tool rotates and the tooth present on its periphery of the tool moving with moving with a velocity v interacts with the workpiece and removes the material in form of chips. Now in ultrasonic assisted milling, with this conventionally rotating motion, we superimpose the ultrasonic motion, ultrasonic vibration motion. Now, this ultrasonic vibration is a conventional vibration motion. It's just a vibration whose frequency is above than 20 kilohertz or equal to or higher than 20 kilohertz. Any vibration which we superimpose here, if it is greater than if it is greater than 20 kilohertz, we will call this machining operation ultrasonic assisted milling process. If it is lower than this, we will call it vibration assisted milling motion. So we are going to see ultrasonic assisted milling process. So in this, we superimpose the in this operation, there is a superimposed ultrasonic motion at the cutting tip simultaneous with this rotational motion. And due to this presence of this ultrasonic vibration at the cutting tip, the cutting mechanism changes. And due to this change in cutting mechanism, the researchers have observed from the experimental data that the average cutting force reduces by a significant amount. It's around 20 to 40%. So due to this reduction in cutting force, the deflection, the tool deflection and all these, like the workpiece deflection, gets reduced, which yields into a more accurate product. Now, due to this increase in accuracy, it can be used for precision machining. However, also, like the researchers have also found that the application of ultrasonic vibration improves the surface quality as well as the tool wear rate. So it looks like it's a win-win situation. If we apply ultrasonic vibration, everything will go up, everything will improve. However, there is a layoff of energy. Like we are spending more energy for generating this vibration. We generally use electrical energy. We use a ultrasonic setup, which takes ultrasonic energy and convert it into vibrational energy. There is an experimental setup which composed of this piezoelectric elements, all these things. So this is specifically designed to generate a vibration at the cutting tip with a like prescribed frequency. Like in our case, it's 20 kilohertz. So it is specially designed setup. It consumes around 1000 watt or 1 kilowatt. So spending this much amount of energy for bulk material removal rate is not recommended. It makes the process uneconomical. So it is only recommended for precision machining, which is generally used for aerospace industry, where accuracy becomes a very major concern. So it is only for precision machining. Why this reduction in cutting force happens can be easily understood by seeing this ultrasonic assisted turning process, because it's a very simple process. Ultrasonic assisted milling process is a complex process. The basic phenomena, it will be very hard to explain. So it's better to understand this, like the same phenomena goes behind the ultrasonic assisted milling process also, but it is very hard to visualize that. So in order to visualize what kind of change happen in this cutting due to this ultrasonic vibration application can be well understood by ultrasonic assisted turning process. Now, here we can see there is a conventional turning operation. There is a workpiece which is rotating at a particular angular velocity, and there is a tool which is going with a specific feed, and the tool is also vibrating along this cutting velocity direction. Now at the cutting tip, if you will see, the cutting velocity is also acting in vertical direction, and this ultrasonic velocity is also acting in vertical direction. If you will see this cutting mechanism in orthogonal plane, something like this will appear. Here the cutting is occurring in this mode. The tool is moving with a cutting velocity, and due to this application of additional ultrasonic velocity, there is a compound velocity, or there is a sum of both the velocities. Now due to this vibration, the tool moves to and forth, like it goes in this direction and it comes back and it moves in opposite direction also. So if you will see this, the velocity of this normal cutting velocity can be given by 2 pi dn, which is calculated by angular, which is like general formula for calculating velocity from angular rotation. And this is ultrasonic velocity, which is generated due to this ultrasonic vibration. It's actually a sinusoidal curve. It has a sinusoidal form. So sometimes it becomes positive and in some cycle it becomes negative. Means the cutting velocity, sometimes ultrasonic velocity acts in this direction, in cutting velocity direction, and sometime it moves in opposite direction. And if the ultrasonic velocity is higher than the cutting velocity, then if the ultrasonic velocity is higher, then in its retraction mode, there will be a separation between tool and workpiece. Okay, so due to this separation, the cutting force drops to 0 because it is not performing cutting operation due to this retraction of the cutting tool. In this time, the tool is not performing any cutting operation, and the tool becomes and the cutting force becomes 0. This reduces the average cutting force. So this is the basic phenomena of this process. However, this happens in very short period of time. It's around 10 to minus 5. This period of time in which like the complete oscillation cycle is around 10 to the power minus 5, somewhere around that. And a small portion in that time, a small portion of in that time, the cutting does not happen and the cutting force becomes 0. However, this has a significant effect on average cutting force, as it has been measured by like all of the researchers which works in this domain, that the average cutting force drops. Everybody has concluded the same thing, that the cutting force drops due to this phenomena. Okay, so this they have termed as intermittent cutting effect. Due to this intermittent cutting effect, this average cutting force drops. Now from the literature, it can be seen the application of ultrasonic vibration reduces the cutting force, improves the machining accuracy, makes the machining more stable, chatter free, or the chances of chattering reduces, and it also improves the tool life. Now after this basic idea about ultrasonic assisted milling process, I will explain what are the model development methods. There are two types of model development methods. One is statistical model and another is analytical model. Now, statistical model, as it can be understood from its terminology, it is statistical. It is based on statistics. It is generally developed from the data which we gather from the experiments. And analytical model are those models which is developed on any concept or any physical foundation. Like there is a physical phenomena. On that physical phenomena, we build a model. That model is known as analytical model and a statistical model. So as an example, it can be seen here. If you want to calculate the cutting force, there is a merchant circle diagram which has a very basic concept about machining. You can Google it, how to it's a I think 30-hour class how to calculate this force, but this methodology can be used to calculate the cutting force. Like here, if you will do the maths, and if you will do the maths using this diagram, you will come up with this formula. Now we by using this formula, we can predict the cutting force. If we change the h, it will give us some response. It will give some cutting force. Okay, so this is analytical model, which is based on this physics. Now, statistical model is generally developed from the data which we have gathered from experiment. Now, if we have performed experiment and we have gathered force data. Okay, on different depth of cut, we have gathered data. We can simply we can simply curve fit it, and we can get this equation. Like here, the cutting force, I have generated this model from a literature. I have used their data points to generate this model. Now, this model, this cutting force model, can also be used to predict this cutting force, and this model can also be used to predict this cutting force. Okay, but both have certain limitation and certain benefits. Okay, what are the benefits and what are the things? Like, it does not based on any physics. Okay, so we don't know what goes behind, what needs to be modified to to use this formula for other prediction. Like, we don't have any information about this strength, because it is mainly developed using the data for depth of cut. It can only be used to predict the response for depth of cut. It cannot be used to predict, so it has a limitation prediction. It can only predict or interpolate data points from which it got generated. Okay, in this model, it can be used to predict any kind of, like, because it's a physics based, we know we have included all these factors which affects the cutting force. If we want to change the material, then we can modify this shear strength and we can predict the cutting force. We can use this formula to predict cutting force. However, this formula cannot be used for any other material or any other specific range. Okay, so like here, if we want to extrapolate this data, if we want to predict this data at 0.6 mm depth of cut, we cannot do it, because we don't know that the trend is going to fall down or it is going to continue going up. We don't know, so we cannot use this model to predict the extrapolated data. Okay, however, this can be used to predict any kind of it can be used to predict cutting force for different kind of material. For, like, it can be used for various processes. Okay, however, the statistical models are more accurate, because it considers it is getting generated from the data. It considers all the anomaly of the process. Here in this analytical model, we are not considering any anomaly like friction. We are not considering, like, there are too many things which we approximate to be ideal, which is not. So statistical models are more accurate, analytical models are lesser accurate. However, it can be used for various type of processes and various kind of material. So its applicability is higher, and statistical model its accuracy is higher. Same thing is written here. So these are the two type of model development. For our case, we are going to study how we are going to develop analytical model for ultrasonic assisted milling process. Now, coming on to the previous literature part, most of the researchers in the prior work, most of the researchers have considered model this effect, this intermittent cutting effect, by calculating this cutting ratio, which is nothing. Like in this figure, we have seen for some time it is cutting, and for some time it is sitting, like it is moving away from this cutting zone and not performing any cutting operation. So the time period in which it is performing cutting operation by total time period is known as cutting ratio. TC is the cutting time, the total time spent in cutting operation, and this is the total time in which machining operation is performed. If we multiply, in literature, we can see that if you will multiply this ratio with this conventional model, in the conventional prediction model, okay, it will yield you the force. It will yield you the force data, or it will give you a good prediction of the cutting force. The researchers have found that the trends produced by or trends obtained by using this methodology has somehow it is following the same trend with the experimental data. However, it is not very accurate because it does not considers the effect of increase in cutting velocity, which is getting generated due to the application of this additional ultrasonic velocity. Also, there is a phenomena called ultrasonic acoustic softening. When you will perform any cutting motion with the ultrasonic vibration, some amount of ultrasonic vibration goes into the workpiece material also. The researchers have, like in separate research conducted by material guys, have found that if we introduce ultrasonic vibration in any material, it becomes slightly softer. So previously, nobody has considered this effect. Also, the model is very basic kind of model, which gives a crude information how this ultrasonic factor is affecting your cutting force. It does not give you very good insight about the this process. So in order to accommodate this acoustic softening effect, as well as this acoustic and this effect of this increase in cutting velocity, or the effect of this ultrasonic velocity on this cutting motion, we have tried to incorporate in our model. So what we have did in this experiment, in the present study, is we have first we have performed experimental study. Okay, without experimental study, no experiments, or you should perform, if you are deriving a new formula, you should have a clear-cut information about the trends of the parameter. Like you should have a clear information how your factors is affecting your response. Without that, the model cannot be developed. Or if you have some basic information or the prior data or prior model, which can be used to bypass this thing. Okay, if you have the pre-existing model, you can modify it for your purpose, or you have to see the data and based on those data, you have to develop a physics, or you have to establish a physics, and based on that physics, you have to develop the model. So in my case, nobody knew, like previously there was no data of acoustic softening, as well as the change in effect of ultrasonic vibration on cutting motion. So in order to accommodate this, I have to perform some experiment. I have visualized it. What are the effect of process parameter on the response, and based on this response, I have tried to develop this analytical model. Before going into this analysis, first you have to check the robustness of your data. Before, if you have a very ambiguous data, you cannot predict you cannot develop a good accurate model. So first you have to check the redundancy of your data. You have to check repetition of the process, whether same data is coming, if you are performing the same operation, the same observation is coming or not. So you have to check the data, whether it is free of any noise. Okay, so after checking this thing, you can perform the analysis, and based on this analysis, you can start doing this analytical model. So same thing has been done here. So I have gathered data, I have analyzed it, and based on this analysis, based on the observations, I have tried to develop an empirical model or method, or like say analytical model for the cutting force. Okay, so while developing this empirical model, there are some constants that needs to be evaluated through experimentation. Okay, so there are some experimentation which to evaluate the constant of this empirical model. Okay, so after using both these things, we can come up with a model which can predict the outcome of this ultrasonic assisted milling process. For further validation, what I have did is I have developed a statistical model based on this experimental data, and I have validated in the specific range whether this whether this model is predicting the response accurately or not. So if it is required after model development to adjust any constant or adjust any parameter to make it more accurate, you have to do it further. Okay, then you will come up with a model which is having good accuracy and can be used to predict responses of this kind of complex process. Same thing has been followed in my case. Like in ultrasonic assisted milling process, what happens is in machining operation, generally we are all mechanical guys. We know the machining is generally the material is generally getting removed from this at this shear zone. Okay, this is based on the piece and panel model, which is a very common model for predicting the outcome of this machining process. We generally say if we evaluate the material property of this zone, we can exactly predict what can be the outcome, what can be the cutting force, what can be the reaction force in cutting this material. Okay, so we have to evaluate for predicting a good model, for developing a good accurate model. First we need to evaluate, or first we need to incorporate this effect, the effect of material property in our ultrasonic assisted milling on our present model. So in order to incorporate this, what I did is I have taken Johnson-Cook model, which is a very common model for material deformation at higher strain rate. So using this model, you can predict the shear strength of a model at given strain rate, at given strain, at given temperature. Okay, if the material temperature rises, it becomes softer, and this shear strength will drop. If you are deforming the material, it will offer more resistance, and the shear strength will go up. So this kind of thing we have to include in our model. Okay, so however, we don't know the exact temperature of the shear zone. Okay, so how to incorporate these things, these phenomena? Okay, without knowing this TR, we cannot exactly predict this shear strength of the material at shear zone. So people have done previously. People have done something like what they have done is they have calculated. They have used a specific model for temperature, like for finding temperature in this kind of machining process, and then they have used that. They have replaced that temperature to calculate the final shear strength of the material. However, it's still inaccurate, because as the material becomes softer, the temperature will rise. Okay, so it will be stable at some specific zone. We don't know. So in order to incorporate this effect, what I have did is I have modified this equation. I have used previously developed equation for strain, which is like these are the developed model for calculating strain in machining, strain rate in machining. These are very already established model which I have used. So I don't have to worry about the accuracy of these models. These models have been verified on different kind of materials. So I have incorporated these models. This temperature model can also be modified into these cutting parameters, which I have considered from Hastings et al. They have also verified it on different kind of materials. So after integrating all these small equations into the bigger Johnson-Cook equation, this becomes something of this sort. This equation becomes something of this sort. Okay. Okay. So using this equation, if we will put any kind of machining parameter, okay, it will give you exact shear strength of the material at shear zone. You don't have to worry about a back calculation or like something else, something of that sort. Whatever you will calculate using this formula, somehow it is going to be accurate as it has. Most of these models have been verified on their specific levels. Their integration may, like, we assume that these integration of these models will also predict the material parameters with accuracy. Okay, so using this model, we can predict the shear strength of the material at the shear zone. Okay. After this, now in order to incorporate, like I've told you that there is a phenomena called acoustic softening. Like if ultrasonic vibration goes into a material, the material will become softer. So previously, material guys has only developed a model. Anybody is having confusion because I'm getting some hello. Okay, so in order to accommodate this acoustic softening effect, I have incorporated this factor, which is acoustic softening factor. It considers the effect of material properties, which is density of the material, velocity of vibration in the specific material, velocity of the or we can say ultrasonic velocity in the material, okay, with which it can travel, the material with which ultrasonic material is vibrating, like the particle or the material or the particle in the material is vibrating. This is the velocity for this. These D and E are the constants which needed to be evaluated experimentally, because it's an empirical model. Most of the empirical model, in order to increase its accuracy, we generally use this model, or in order to fit this empirical model for our purpose, we use this constant, and this needs to be evaluated through experimental data. So in order to do this, I have performed some ultrasonic assisted tensile test. So in this test, what I have did is, I have during the tensile test, I have superimposed ultrasonic vibration using this horn and this generator. So while getting stretched, I am applying ultrasonic vibration in the material. So if there is a material softening, I will be able to capture by evaluating this data. So after evaluation, I found that as I have increased the amplitude of ultrasonic vibration or ultrasonic power, the yield strength of the material gets reduced, or the yield of the material drops. Now it can be seen, it is only I have only applied the ultrasonic vibration in this specific zone, because as suggested, the ultrasonic velocity must be applied in yield zone only before ultimate tensile strength, because after ultimate tensile strength there is a localized deformation kind of thing, which which we don't want to include in our model. So in order to predict the effect of ultrasonic vibration on yield strength, we need to apply the ultrasonic vibration between yield point and ultimate tensile point. This is the true stress and true strain curve. That's why UTS is not coming. It's cut. And if you will plot its UTS, engineering stress and engineering strain, the ultimate tensile strength will come somewhere around here. So I have applied the ultrasonic vibration in between that to predict to evaluate this constant accurately. Okay, so using that model and this experimental data, I have also evaluated the effect of strain rate, whether this factor D, whether these two factors, acoustic softening constants D and D, are getting affected by strain rate or not. So, like in this thing now, in this tensile test, there are two parameters which can be varied. One is strain rate, and another is ultrasonic power. So we have checked both this effect so that we can exactly capture we can exactly evaluate these constants, or if required, we can modify it in order to incorporate the effect of strain rate also. Luckily, in our case, the effect of strain rate was not there, so we can use this model directly by evaluating these constants. So what we have did is we have curve fitted this model, okay, and we have, using this curve fitting thing in MATLAB, we have evaluated constants D and E. Okay, so these, after getting these constants D and E, everything rest of the thing is either material property or cutting parameter. So if we incorporate all these variable, which is cutting parameter, and all these constants, which is either material property or the outcome of this experimental data, after substituting all these things in this equation can directly be used to predict the shear strength of shear zone in ultrasonic assisted machining operation. Okay, so what we did is we have used this equation to predict the shear strength of material of shear zone. Further, this calculated data was used to calculate the cutting force. Okay, so this is the effect of ultrasonic vibration on material. Further, we have included the effect of ultrasonic velocity on cutting kinematics or cutting mechanics. Like, due to this ultrasonic vibration, in ultrasonic assisted milling process, what happens is, as we can see from this thing, the tool is rotating in this direction and it is vibrating in axial direction. Okay. If we evaluate the cutting velocity at the cutting tip, okay, then something of this sort will appear. The ultrasonic velocity is occurring in axial direction and the cutting velocity is occurring in tangential direction due to this rotational motion. And because of this helix, the actual cutting direction becomes like this. Okay, if you will superimpose, if you will do some mathematical calculation, if you will transform it in this along the helix angle and perpendicular to helix angle, this ultrasonic velocity and this normal velocity can be transformed in these two directions. And this ultrasonic, in this transverse ultrasonic velocity, we are actually interested in this transverse ultrasonic velocity. Why? Because if due to this transverse ultrasonic velocity, if the velocity in this direction rises due to ultrasonic vibration, like it is, if the velocity in this direction gets increased, it will result into separation of tool and workpiece. Okay. So in order to capture the exact this intermittent cutting effect, we have developed a model which is can be given by this. It's like you can go through, like I will give you the paper exact what is the basic of this developed model, this development of this intermittent cutting ratio, or the cutting ratio, or the cutting time, how this is developed. You can go through my paper, how I have developed it, and using this formula, this cutting ratio was developed, and using this cutting ratio, we can directly multiply, as it has been suggested by most of the researchers, that if you will multiply this cutting ratio in the cutting force, exact in the conventional cutting, in conventional milling force, it will result into a prediction of cutting force of ultrasonic assisted milling process. Now, as we can see, it does not require any kind of evaluation, any kind of constant evaluation. It is mainly given by Vn, which is due to rotation, and ultrasonic velocity, which is dependent upon the frequency of the vibration and amplitude of the vibration. So all these things are known. All these things are parameters which we can control in the process. So using this formula, by multiplying this formula in the conventional cutting force, I have predicted the ultrasonic cutting velocity. Now, in order to accommodate the effect of helix angle, in order to accommodate this, what I have did is, because whatever model I have used to calculate the cutting force, it's generally everywhere in milling operation, like here the cutting operation is going on, the tool is moving in this direction, in horizontal direction. Okay. So at every place the chip thickness is different. So we cannot calculate the exact cutting force by considering the any specific chip thickness. It needs to every chip thickness needs to be evaluated separately, and the cutting force at each and every section must be evaluated separately, and these things can be added together to predict the average cutting force of this milling operation. Okay, so in order to do so, I have divided this tool into different sections and different slices or different layers. Each layer has a thickness of 0.1 mm. And now for this much amount of thickness, we can say the chip thickness is constant. Like for this much thickness, for this much layer, chip thickness is constant. For this layer, chip thickness is it is different from this layer, but it is constant throughout we are taking average. Okay. So after segregating this tool, after calculating in segregated way, we are able to calculate, catch the effect of helix angle. And after calculating this cutting force using this methodology, we have used a very previously developed model for milling process, which considers the same effect. Like they have also, what they have did is they have also sliced the tool, and they have calculated the cutting force for each slice, and they have added it together to calculate the cutting force. I have used the same methodology. The new thing about this, my model, is just two things. One is acoustic sorting effect behavior, and this cutting mechanics, explanation of cutting mechanics, how to calculate it, and how this helix angle is affecting this intermittent cutting effect, and how this other parameters is also affecting this intermittent cutting effect. If you will see here that if you will change this is the cutting time. This is the total time of ultrasonic vibration. This is the total cutting velocity. If we will plot this cutting velocity, VUL plus this one, this total cutting velocity here. So if we will, due to this, and if we will simulate this cutting velocity by considering VUL max in place of this this VUL max, okay, and VUL max is 2AF. If we will change for if we will see the total cutting velocity of the tool with in the span of this time, which is very less, it's microseconds, 2 to the power minus 5 second, to the total time of this ultrasonic velocity of this one oscillation is around 5 into 10 to the minus 5 seconds. So for this period, only for this period of time, the cutting velocity is becoming negative, means the cutting velocity is in opposite direction, or it can be said the tool is retracting from the cutting zone. Between this period of time, the cutting force becomes 0, and the ratio of this cutting zone, which is this plus this. So this cutting time by total time is known as cutting ratio, which we have calculated through this formula RC. So by incorporating all these effects, this kind of formula has been generated. It consists of RC, this cutting ratio. It also for capturing the effect of acoustic softening effect. This R actually consists here in shear strength. We have used the formula. Which is developed here. This TB, tau B. We have used this formula here to calculate the exact response of the material. And RC has also been included in order to incorporate the effect of ultrasonic vibration on cutting mechanics. So all these three factors have been incorporated together to predict this outcome, this cutting force. Using this cutting force, we can predict. Then we can exactly predict the cutting force, cutting force of ultrasonic assisted milling process. So in order to check its accuracy, you need to perform experiments. Okay. So in order to perform experiments in ultrasonic assisted milling process, first you need to develop a tool, because in the conventional tools does not vibrate at such a high frequency. You need to design a specific tool in order to execute such a high frequency with cutting operation, in this cutting operation. So in order to do so, first you have to simulate, first you have to do some basic calculations, which you will find it in any horn like if you will go through the calculation for designing a horn, you will find the basic calculation over there. After designing the specific calculating the specific those values, we can develop this this model. We can develop this CAD model, and using this CAD model, we can perform this modal analysis. Now, what this modal analysis does is it gives its natural frequency of the setup. Using this natural frequency, you can identify whether this whether it will vibrate at its maximum, whether it will yield maximum amplitude at given frequency or not. Like if you are designing this tool for 20 kilohertz, it should have a natural frequency around 20 kilohertz. It's not exactly, it should not have exactly 20 kilohertz, but it should have somewhere around 20 kilohertz. It can be 20.001 kilohertz, somewhere around that. But it must have somewhere around that thing. It must have a natural frequency somewhere around that. So by modal analysis, what we can do is we can fine tune it. We can change the length, or we can change its shape to exactly get a modal frequency of 10 to 20 kilohertz. So designing this specific frequency, after designing the specific horn for this specific frequency, we have to perform some harmonic analysis. In this harmonic analysis, what it will give us the amplitude factor. If you are applying ultrasonic, like in ultrasonic vibration, what generally happens is there is a piezoelectric element, okay, which uses electrical energy, and because of its material property, it can convert this electrical energy into vibration energy. Now, using this horn, now this amplitude which we get from this piezoelectric material is very less. In order to amplify it, what we do is we design our setup something like that, what we are designing. Okay, so through this, we are actually amplifying the vibration which is coming from this end. Okay. So after this thing, harmonic analysis will give how much amplification factor we are getting from this this designed harmonic setup. If it is 5, like if the amplification factor is 5, so this means that if our piezoelectric material is generating a vibration of 5 micrometer, then it will multiply it with 5, or it will generate somewhere around 10 micrometer of amplitude at the cutting tip at here. Okay, so it's the basic, this simulation basically gives this thing. Okay, further we also have to check like whether during this simulation, during this vibration, the material expand. Like we all know, when sound vibration travels in a material, the material gets a specific portion. When the vibration passes from a specific zone, it observes tensile as well as compressive stress. Okay, due to its motion, due to its the basic methodology. This is the basic phenomena with which this vibration travels. The material generally observes compressive as well as tensile force. So first we need to evaluate whether while this motion, whatever vibration, whatever stress getting induced due to this vibration transmission is exceeding the yield strength or not. If the stress generated due to this ultrasonic vibration transmission is higher than the yield strength, then if you will apply this vibration in this thing, then it will deform permanently. It will not be used. It cannot be used. So maybe it will result into a crack, or this tool will permanently deform. It cannot be used for. So we have to check whether the stress which is getting induced due to this vibration transmission is lesser than its yield strength or not. After confirming that the yield strength is less than this thing, yield strength is less. This generated stress is less than yield strength. We can say that this developed ultrasonic horn is suited for ultrasonic assisted milling process. Okay, if it is not coming as per our requirement, then we have to design it again through, like it is a redundant process. It's like you have to do it again and again so that you can get a final shape suited for your application. Okay. It's a repetitive work kind of thing. Okay, so in my case, that is my simulation. I have actually validated all these things. Whatever I have explained, I have validated all these things. I have fine-tuned my tool in order to get these results right. After getting these results right, correct, I have developed actually this tool. This tool directly can be mounted on CNC milling head. Okay, this is the horn. Here, this horn is exactly this portion. Okay, so using this horn, there is a piezoelectric element stacked inside this casing, and these are the copper rings. Okay, through which we are trying to supply electrical supply to those piezoelectric elements. So if you will see the schematic of this thing, these are the piezoelectric elements. These are the elements stacked inside this thing. This is the copper. This is this casing which in-houses this piezoelectric element. These are the copper rings which can be seen here. Through this copper ring, we are supplying electrical supply through these wires, in order to excite this ultrasonic, in order to excite this piezoelectric element to produce the vibration. Okay, so using this tool, this tool can directly be mounted on CNC milling head, and further we can supply the electrical power supply, and we can perform this ultrasonic assisted milling process. Same thing has been done here. See here, ultrasonic assisted milling process. We have, this is a power supply where where this carbon slip rings are there, carbon brushes are there, through which we are trying to supply electrical power supply to this piezoelectric elements which is encased inside this casing, and we have mounted this complete thing on CNC milling head so that the rotation can also be given. For measuring the force, we have used dynamometer. We have fixed our workpiece. We have used Shunk dynamometer for this purpose. We have mounted our workpiece, which is aluminium AL6063. We have used AL6063 because its machinability is slightly poor. Also, it is very common. It's very common. It has a very common application in aerospace and aerospace and this aeronautics industries because of its low density. Okay, so in order to check its cutting response, we have machined ultrasound AL6063 aluminum alloy, and we have measured the cutting forces. Now, before processing the experimental data, first, as I have said, first you need to evaluate the experimental data. You have to check whether whatever you have captured, whatever data you have captured is correct or not. Whether data, what you are capturing is able to capture what you want to capture. Okay. Means, if you want to capture the effect of ultrasonic vibration, the effect of that ultrasonic vibration should reflect on this experimental data. Okay. In order to do so, we have to perform some analysis on the experimental data. Like I have performed FFT analysis, fast Fourier transformation. What it does is fast Fourier transform analysis. It transforms the signal into frequency to the frequency domain. Using this frequency, it's not whatever I have said. It's not exactly that. However, it is roughly. It can be said that it does this thing. Okay, it takes the data from time domain and it transforms to frequency domain. So using this FFT analysis, you can say what kind of frequency you can see in your, what is the kind of frequency you are capturing in your data. If the cutting force, as I said here, that the cutting is intermittent in nature. In every cycle here, in every cycle, in every cycle, this sorry, yeah. In every cycle, this separation take place. Separation takes place means the cutting velocity, the cutting force will go from maximum to zero suddenly. Okay, so it will have an impact on the data. It will go from maximum to minimum, maximum to zero. So there must be a frequency in your data which respond to this, which must respond to this intermittent cutting, okay, or this separation of tool and workpiece, and that the frequency of that thing, this must reflect on your data, or like I can crudely say, you should get a peak in your FFT analysis at 20 kilohertz, because in each second 20,000 times your tool is separating from the workpiece zone, and again it is start performing cutting operations. So this transformation from maximum to minimum happens 20,000 times in 1 second. So that thing must reflect on your data. So in order to see whether that thing you are able to capture or not, because if you are not able to capture this thing, your experimental data is not correct. You have to check whether whatever effect or phenomena you want to capture, if you are able to capture the frequency of that phenomena, then only this data can be used for further processing. Otherwise, you have to increase your frequency range, or you have to check your experimental data, or you have to do some modification in order to capture healthy data for further processing. As we can see, I have also done the same. Like previously, I was capturing experimental data at a frequency rate of 20 kilohertz. Then I have to go through some literature. Then I found out that I have to follow some Nyquist criteria, that at least whatever frequency you want to capture in your experimental thing, your sampling rate must be higher than twice of that thing. Okay, so if I want to capture 20 kilohertz of sample frequency, then my sampling rate, my capturing rate, data capturing rate must be 40,000 kilohertz or more. Okay, so after checking the data, after like adjusting the parameters so that we are getting a healthy data. So after getting a healthy data, it becomes you have to evaluate the effect of process parameter. Okay, because if you want to check the accuracy of your model, you have to see whether it is predicting the correct things or not. If you are using your model to calculate the cutting force at different parameter, say the trend which you will get from here must match the trend from the experimental thing. Okay, so we need to develop a model, a statistical model, in order to check the accuracy of the developed theoretical model. Okay, so in order to do so, we have used a very common methodology, which is surface response methodology. In this why we have considered this surface response methodology? Because it gives the effect of higher order terms. Like it can give it generally yields equation of this kind. Now x is your parameter, x square is your higher terms. We can also use Taguchi and other methods, but Taguchi only gives the linear effect of the parameters. Also, if you will follow this as full factorial, the number of experimental runs increases. Okay, so in order to get optimum, like you can get a optimum model with minimum number of experimental runs using this surface response methodology. In the surface response methodology, I have used experimental design called central composite design methodology. Using this design methodology, I have designed my experiment. Okay, for designing experiment, you must know that your experimental range and levels, because what it does is it will arrange your experiment in such a way that you have to perform certain experiments at certain parameters, and it will give you the exact model which can be used to predict your response in that specific domain, any parameter in that specific domain. Okay, so in order to do so, you must evaluate the process parameter which have effect. Like there are many parameters. Now even environment has an effect on our response. If the temperature is very high, your response will change. If the temperature is very cold, your response will change. So we cannot accommodate those things in our model. So first, in order to evaluate this thing, what are the main factors which are affecting my response? We have to perform some parametric study. We have to check what are the parameters. We have to like vary each and every parameter of your process, and you have to check what are the parameters which is exactly affecting your response. If it is not affecting your response, you should not consider while designing your experiment, because it will increase the number of runs and it will not give you any benefit because it does not have any effect. Okay. So after performing these preliminary experiments, I have gathered the effective parameters which is affecting my response significantly. I have also, using the data of this preliminary experiments, I have also evaluated what is the experimental range in which I want to evaluate the thing. Like if you will see general theory, any theory, in like if you will vary a parameter, some parameters are like that if you will vary it, your response initially your response will be stable, and suddenly it will vary very abruptly, and then again it will become stable. So we want to evaluate this variation, why this variation is happening. Okay, so we have to choose our experimental range such that we should capture these variations. So the effective range must be evaluated through this preliminary experimentation. So I have done it by performing lots of preliminary experimentation. I have very different parameters. I have also very different. I have experimented on different range of process parameter, and finally, by analyzing the result, we have come up with this range of process parameter. Okay, for designing by designing an experiment using central composite design methodology, you require 5 levels at least. You require exactly 5 levels of your process parameter. So you got your range of experimental data where you want to evaluate a process parameter. You have to divide it evenly. This range, this levels evenly, so that the difference between these levels should be even in all these things. Okay, so we have distributed. We have just selected the levels. We have divided these parameters into specific levels, and using these levels, we have designed these experiments using central composite design methodology. We have performed experiments, we have captured the data, and using this data, we have performed ANOVA analysis. Like if you will see, there are tons of videos available on YouTube how to do this ANOVA analysis and how to use this central composite design methodology. Using these design methodologies, you will come up with, I have come up with these formulas which can be used to predict, which can be considered as statistical models. Okay. And using this statistical model, you can predict your cutting forces at in this specific range. So after getting these equations, we have used this equation to predict cutting forces, as well as we have used this model to predict cutting force in the same range. Okay, so it can be seen that at macro scale cutting, okay, in micro scale cutting, the accuracy of the model is higher. Macro scale cutting, the accuracy of the model is higher because it is not having very high accuracy in micro scale cutting, because as I have said now, all the analytical model is based on some physical phenomena. If we will integrate all the physical phenomena in this model, it will capture most of the things. However, in this model, we have not captured the effect of friction and the effect of vibration on the friction. Okay, we have not considered both these effects, which has very significant effect on at micro machining level. That's why this difference in the predicted and experimental things coming. However, in macro scale milling, macro scale machining, this effect of which is generally this effect of this friction is generally termed as scale effect. It becomes insignificant, or its significance becomes less for macro scale machining. Okay. So as you can be seen that the model has a good accuracy in case of macro scale milling. Here also, if you will go through this complete chart or this complete experimental result, you will find whenever you will go for micro scale machining, the model becomes inaccurate. So from this experimental data, we can see for micro scale machining, it becomes very important to evaluate the effect of friction on in this ultrasonic assisted machining process. It's our future work. It will be done in my future research work. However, as of now, I can say that the developed model has a good accuracy for macro scale ultrasonic assisted machining milling process. Okay, so I have also compared this result with the experimental and predicted result, which we have calculated using our analytical model. The error percentage is very less. It's around 6.5. It's less than 10%. So it is considered very good in case of analytical machining, because analytical machining, we are in analytical machining, we approximate too many things. Okay, that includes too many different type of error. Like in my case, I have not included the effect of friction. That included error for micro scale milling. Okay, so for in analytical model, we cannot accommodate each and everything, because accommodating each and everything requires too many experiment, evaluation of too many constants, and performing too many of experiments. Also, this will result in very complex model. If you will incorporate each and everything, the model will become too much complex. Okay, it will be not good for use for industrial purpose. So in order to keep this model simple, you have to approach too many things. And we can specify, okay, with this consideration, with this approximation, this model is valid for this specific range or this specific zone. Okay. However, this model can be used for different type of materials. Okay. We can use this model for this conventional milling operation also, because if you will just we use the, if you will remove the value RC, or if you will put value of RC, if you will take like one unity value of RC, this formula will work, or this formula will work for conventional milling operation also. So this is the benefit of analytical model, because we know what are the things that needs to be manipulated, or what are the parameters, or what are the constants that needs to be manipulated in order to transform this model for a specific use. So after this thing, we can say the developed model has good accuracy and can be considered for macro scale ultrasonic assist for prediction of cutting force for macro scale machining processing. Okay. These are the publications. You can go through it and see if you want any reference, or if you want any detailed work, detailed explanation of anything what I have said. You can go through this thing, any of the paper, and you can check, you can go into the detail. Okay. Apart from this, I can say that I've also developed a model for thermal for prediction of thermal. Same thing has been used, but for the calculation of thermal, it's slightly different. However, the time is not suitable. Like the time is not enough to discuss all these things, because we have to, like, I have to answer some of your queries also. So so after this thing, I conclude my presentation. Now I ask all the participants to ask me any query relevant to this thing. If you have any kind of query, kindly just okay. So I'm done with my presentation. So if you want, you can ask me any query relevant to this topic.
So there's a question from YouTube chat.
Okay.
That can the process parameters be optimized using response surface method, RSM?
Yes, like it's a equation. It's a equation. Both the equation can be used to optimize the process. However, as I have said, the statistical model has a limitation that it cannot extrapolate. It cannot predict the extrapolated data. If the optimum parameter is lying apart from this experimental zone, we cannot predict the optimum range. Statistical model can only be used to predict optimum range in the given, like in the parameter you have considered for your experimental thing. Only in that range you can optimize the process. Like I have done my experiments in this specific range. So my process can only be optimized in this range, in this rotational range, or in this in this feed range, or like in this specific range in which I have performed my experimentation. In only that range, I can optimize the process. However, analytical model can be used to optimize at a wider range of process parameters. This is a basic difference between analytical and statistical model. But yeah, it can be used to predict. It can be used to optimize process for a specific range.
Sir, next question is from Mr. Shiv Kumar. That the tetrahedron mesh has been done for whole model or by selecting particular intricate parts in the 3D model?
For simulation, the complete thing is not modeled, because we are what in this ultrasonic assisted this modal analysis, what we say modal analysis, what we are trying to see whether whatever I have designed for my experimental setup is giving me that exact exact effect or not. Like I want to maximize my amplitude. So I only considered I have only considered the simulation for horn as well as tool, because the vibration is coming from piezoelectric element, and it is from piezoelectric element it is getting transported, or it is transmitting from horn through the tool. So I have only analyzed that portion, and for that complete portion I have used that machine.
Thank you, sir. Sir, another question is from Dr. Rajesh Joshi. That
Yes.
could you comment about the tool life in UAM compared to the conventional milling?
Actually, there is a I have not evaluated the exact thing, but as of now, if you will go through the prior research work, you will find that many of the research work have commented that thus at a specific range of process parameter, this affect the tool wear reduces. In some cases, in some range, it may worsen your case, or it will produce higher defects, or it will increase your wear rate. Because of this intermittent cutting thing, this tool this interaction between tool and workpiece becomes abrupt. If you will perform this intermittent cutting at very lesser cutting velocity, this engagement and disengagement becomes very abrupt, which generates shock kind of thing on the tool surface, and which is very harmful for the tool surface, and further it leads to tool wear, faster tool wear.
Thank you, sir.
I'm not able to hear any of you.
No, sir. I can't find any other question.
Sir, I'm not able to hear.
Okay. Thank you, Dr. Girish Verma, for accepting our invitation for this talk. You explained very well about the modeling of ultrasonic assisted processes, milling process, turning process, modeling of ultrasonic assisted machining process, in which mathematical modeling of UAM forces, cutting kinematics, some simulated techniques, experimental study of UAM forces. Thank you very much again.
Thank you.
Over to you,
so much
Subodh.
for inviting me.
Okay.
Any
Thank
other
you.
question from any of the participants? If there is any, I will answer. Or it's okay then. Okay.
Thank you again.
Okay. Chat box. Okay. I will share this thing. Okay. So this is my email ID.
Okay.
Okay.
Thank you once
so
again.
much.
Thank you.
Thank you so
Okay.
much. Thank you so much for inviting me. Bye.
Hello.
So shall we leave?
Okay, sir.
Shall we
Okay.
leave and
We will meet. Yes.
Okay.
We will meet you on 4:15.
Okay. Thank you.
Okay. Okay.
Morning I joined on YouTube only, but here morning there was network connectivity problem. But
Okay, no problem.
afternoon session, afternoon it was there. I can join. I could really join. Morning I
Okay.
joined on YouTube.
Okay, no problem, sir. No problem.
Okay. Okay. Yeah, no. Today there was a network problem. That's why I joined on YouTube. Okay, sir. Thank you.
Hello, sir.
स्क्रीन शेयर क्यों नहीं हो रहा है? नहीं सर, नहीं सर, नहीं सर, नहीं सर, सुन रहे हो? स्क्रीन शेयर नहीं हो रहा है, एक बार लीव करूं, मीटिंग फिर से ज्वाइन करूं? ना एक मिनट, जस्ट लीव करता हूँ फिर ज्वाइन करता हूँ। Should we start now? Okay. Okay.
Okay, sir. Yes, sir, I can see the screen now.
Okay, just a minute. Okay. So good evening to all. Can you listen to me?
Yes, sir. Yes, sir.
Am I audible?
Yes.
Okay, thank you. So I have shared the. Yes.
Yes, sir. A very good evening to everyone present here.
Okay.
This session is on the topic finite element model updating and dynamic analysis. For this session, we have with us Dr. Manoj Choksey, sir. Sir, you are an associate professor in mechanical engineering department at SGSITS Indore. You have received your PhD from Indian Institute of Technology, Delhi. and you have many research papers in reputed international journals on the topics of model analysis, vibration engineering, and rotor dynamics. You are a member of a number of professional bodies and have guided students for PhD. Now, I would request you to please commence with the presentation.
Thank you, Subodh, for the introduction. So now I start the presentation. I will share the PPT. I am audible, and you can see the PPT.
Yes, sir.
Okay. Okay. So the topic of my presentation is checking accuracy of results of finite element analysis. Yes. Uh, we generally use finite element method to model various systems. It may be static system, dynamic systems, and this method has applications in various disciplines, not only in mechanical engineering but also in other disciplines like biomedical engineering. So, but generally, what we do, we model the system and find out its results. But it is also important to find out the accuracy of the model, because uh, we engineers always try to model the physical systems, the actual systems, and the model should be such that the results that we get from the finite element model should match with the experimental results. So how can we do it? What are various ways so that we can rely on the results of finite element analysis or the finite element model of the components that I am going to discuss with the presentation. So various ways of checking accuracy, I have listed here 3 points. First is the convergence check. Convergence check is very important when we carry out finite element analysis. And it happens that many people do not know about it. What students do, they will, what people do means, particularly students, they will model the physical component, they will carry out the finite element analysis, and they will find out the results. But when we ask about whether the results are reliable or accurate or are correct, then they do not have the answer. First and foremost thing with finite element analysis is that I believe that you know finite element analysis. First, finite element method or finite element analysis is a numerical method, is a numerical technique uh, where we model the actual system first. First is the physical, first is the modeling, and then we discretize the system into various components, small components of finite length, because we are discretizing the actual object or solid model or the line model into various sizes of definite length or definite size. Therefore, we say it finite element method because the size of the elements are finite. So, what is convergence check? First, we should do the convergence check. For example, I will use convergence check with one example. Okay, then you will understand that what is convergence check. It is very important to apply the
We are having some technical issues and the presentation shall resume very soon, so please stay tuned.
Okay. Okay, it is now on. Okay. Okay, okay. I okay, PDF शेयर रहेगा ना इसमें? ठीक है. Okay, thank you. So you can see this. So what is convergence check? PPT is not shared. Okay, just a minute. Now PPT is shared. Okay. Okay, you can see the PPT. Okay, so just I want to convey you a few concepts like of the convergence check. This, this convergence check is also called grid independence test and CFD. So what we do here in convergence check, we start with some size of the element. For example, for this problem, we started with this size of 0.3 meter, and then we took 0.1 meter. When we decrease the size of the element to 0.1 meter, the results of the bending stress were decreasing. So, on which result can we rely? On this one or this one? On and not on any of these two results we can rely. So we try to reduce the size of the element, or we just double the number of elements. Okay, and then you can see at this size of the element 0.001 to 0.0005, the results are converged. Okay, are you listening me, Ganesh sir? Okay, okay, thank you. So we just check for two consecutive results, so that the difference between those two results is negligible or very small. Or we can set here some model that the results should be means not more than the order of the 10 to the minus 2 or 10 to the minus 3. In this way, when we set this size, we can rely on either this element size or this element size. So this is the first and foremost check that we should do in any finite element analysis. And next, what we are doing here for this simple case of fixed beam or simply supported beam, we have compared here the results that we obtained by ANSYS listed here of the bending moment, stress and deflection, and theoretical results are obtained here: bending moment, stress and deflection. And we found out the error. Here error you can see here, error is of means almost zero here in few cases, and not more than 3.8%, 1.9% for some results. So in this way, such a comparison gives some confidence that what we are doing is correct. But these are for the simple cases. What to do for some complex cases where we do not know the analytically obtained results, because you know that finite element analysis or finite element method we use for some complex systems where we do not have the analytically obtained results, or we don't have the closed form solutions. So for such problems, what we do that I will tell you. But whether it be a simple problem or it be a complex problem, convergence check is must. So after carrying out any finite element analysis, we should we must, I should say, we must means check it for the convergence. If the results are converging to some value, then only we can rely on such results. Now, in convergence check plot, what we do on the x-axis, we write the number of elements, size of the element. On the y-axis, we can plot any result which you are focusing. Like if you are finding out stress, you can write bending stress. If you are finding out deflection, you can write the deflection. If you are finding out natural frequencies in dynamic systems, then you can write natural frequencies there. Okay. Now, these are some plots of the fixed beam. This is the stress plot here. On the fixed ends, the stress is maximum. You can see with this red colored Here stresses are maximum, and there is the graph for deflection of fixed beam. So deflection is maximum at the center. So such plots can be drawn for the analysis. Now this is a simple table, corresponding table for for the supports when we consider them simple supports. So simply supported beam, the stress, bending moment, deflection are compared of the answers with the corresponding theoretical values, and the percentage errors are found out. So I told you about two things. First is the confidence check. Second is we can compare the results of simple systems with the analytically optimal results. But then for what to do for complex systems? So how to rely on models, finite element models, when we are modeling some complex systems? So here comes the importance of dynamic analysis. Dynamic analysis, we also say, is the vibration analysis. Okay, and ANSYS, there are many ways where you can carry out dynamic analysis, like you can carry out model analysis, harmonic analysis, transient analysis, and so on. So mechanical vibrations, just simple introduction. Vibration is a mechanical phenomenon. To and from motion of any object about some mean position, you say, are the mechanical vibrations. So it is simple introduction. Vibrations are both desirable and undesirable. I often tell one example of Tacoma Bridge, failure of the Tacoma Bridge, to understand the problem of the importance to study the dynamic analysis. This bridge was inaugurated November 7, 1940, and within few months of its operation, the bridge collapsed. And the good thing is that we have a simple video how this bridge collapsed. You can see here how the bridge collapsed. And it was simply said that two theories are given. One is the theory of resonance, and second is the theory of instability or wind-induced excitation. Here we say that the wind was flowing across the bridge, and when and these swirls were formed, and when the wind excitation frequency matched with the natural frequency of the this structure, there was resonance. And you can see this video. At that time in 1940s, this video was recorded, and how this bridge collapsed. Okay, so you can see how this bridge is oscillating, and this one truck coming over the bridge, and it is experiencing such great oscillations. So how can we use dynamic analysis to ascertain the accuracy of the finite element models? This I am going to tell you now. So this is the failure of a rotating machine, how it collapsed due to excessive vibrations. So what is model analysis? So we can use the theory of model analysis to check the accuracy of the finite element model. How can we do that? I will explain you this. So first you need to understand what is model analysis, MODAL, model analysis. Hope you can listen me. Okay.
Yes, sir. Yeah, listen. We are listening, sir.
Okay. So model analysis, there is one term, MODL, model, and this is MODL, model. So model analysis is made from the word MOD, mod. So for dynamic systems, we have natural frequencies in mod shapes. Okay, natural frequency is the frequency of free undamped vibrations, and the mod shape is the corresponding deflection pattern of that structure corresponding to that natural frequency. So here you can see for a simple plate, there is the first bending mode, there is second bending mode. Hello? Pardon, sir? Okay. So you can see this screen. So in model analysis, we find out natural frequency in mod shapes of any structure. So natural frequency is the frequency of free undamped vibrations, and mod shapes are the deflection pattern of the structure corresponding to any natural frequency. For example, when this plate is vibrating at first natural frequency, then it is first mod shape. When it vibrates at its second natural frequency, it is second mod shape. When it vibrates at its third natural frequency, it is third mod shape, and then we have the fourth mod shape. Okay. So model analysis is based on various assumptions like linear system theory, principle of reciprocity, and model analysis is classified into two parts. One is theoretical model analysis, and second is the experimental model analysis. The theoretical model analysis is like if we carry out it using analytical methods, or if we carry out it using softwares like ANSYS, Nastran, then we keep it under the category of theoretical model analysis, right? And when we find out the natural frequencies and mod shapes of any structure by experiments, by measurement, then we say it experimental model analysis, also termed as model testing. Okay, so it is written here. Here we perform the test on the actual structure, and how we do that. Here you can understand that with few examples. Like I told you this definition, we find out dynamic properties of the structure with model analysis. And why is it important? It has many applications. Model analysis, model testing, experimental model analysis has many applications. Few are listed here: aircraft, automotive industry, consumer products, civil structures like bridges, sports equipment. You can see here this shaker exciter is being used to excite this structure so that we can measure the natural frequency using the accelerometers here, mounted here, right? And the next here you can see here wind turbine blades. Many accelerometers are mounted on the wind turbine blades.
Hello? Hello? Joxer sir is there? Number नहीं है. Hello, Choksey sir. Hello, Choksey sir. Yes, yes. I talked him.
Okay.
Sir, mic on करिए.
So here this beam is mounted with many accelerometers and this shaker exciter. It is full screen, na?
No, it is not.
Okay, just a minute. Okay. Okay. Now it will come. So this is the example of shaker exciter. Many accelerometers are mounted on this beam to measure the mode shape displacement pattern. And shaker exciter, as we excite the structure, we measure different frequency response functions, and then we measure the corresponding mode shapes. You can see this is the first mode shape of this free beam. This is a free beam, the first mode shape, second mode shape, and a third mode shape. Okay. And similarly, impact hammer is another instrument which we can use for excitation of the structures. Like here, this Heavy rotor shaft is being excited with this impact hammer to measure the natural frequencies in mod shapes. And this another machine here, and the aircraft wings are being excited. Here this motor is being excited to measure the mod shapes and the natural frequencies of the structure. So at this end the transducer is there, force transducer is there. As we hit this on the structure, the impact loading, we do impact loading, and the corresponding force is measured, which we send it to the FFT analyzer. Okay, are you am I audible? Can you listen to me?
Yes, sir. Yes, sir. Yes, sir.
Okay, now how with the help of hammer test we find out different mod shapes. Like with hammer test we have mounted one accelerometer here, because you know many times we do not have many accelerometers. Then like in previous example we had to mount many accelerometers because the excitation point was fixed. But if we have single accelerometer and one impact hammer, with this set we can perform the complete model testing. So what we do, we mount the accelerometer here and we use the impact hammer and impact it at various points one by one like this. So instead of measuring displacement at various points, what we are doing, we are exciting the structure at various points. So both methods are fine, but this method has the advantage that we do not need many sensors here in this method. Okay, because the systems are linear and the principle of reciprocity holds. That is why it is possible that we can adopt any of the methods for the complete model testing. So again, we extended here first mod shape, second mod shape, and third mod shape, as you can see. Okay. So again, model analysis definition is there. So with model analysis, what we find out? We find out eigenvalues and eigenvectors. Okay. So eigenvalues include any of the eigenvalues include the real part and the imaginary part. As you can see here, the imaginary part of the eigenvalue gives the natural frequency of the system, and the real part of the eigenvalue gives the information about the stability of the system. Okay. And from these eigenvalues we can find out the model damping factor. As you have learned in vibrations, you might have learned in vibration engineering that any system can be underdamped, overdamped, or critically damped system. So if any mod is underdamped, overdamped, or critically damped, that we can find out with the help of this model damping factor in RF mod. So here we use the information of the eigenvalues like the real part and imaginary part to find out the corresponding model damping factor. Okay, and model of any system includes the natural frequencies, damping factors, and mod shapes. So various ways may be there to represent any system. Like we can represent any system by its stiffness matrix. This is one method. Second method is that we can represent the system by natural frequencies and damping factors and mod shapes, because these are the properties of the system, and these things does not depend. These things are not dependent on the excitation forces. And third way is that I have not explained FR, frequency response functions. So what is the need of model analysis? Ensuring structural integrity requires knowledge of dynamic characteristics of the system. Model analysis helps in understanding system properties like natural frequencies and mod shapes and frequency response functions. It helps in identifying possible resonance regions of the machine. So we know that any machine should not vibrate under the phenomena of resonance. So if we have to avoid the phenomena of resonance, then we should find out the natural frequencies of the system. Otherwise, how will we know that what should be the operating frequency range and which range we should operate the machine? Model data can also be used in dynamic design. So many times it happens that a particular machine is resonating under the existing conditions. Then if we have to operate it, then at the operating speed under the present condition, under the present stiffness or flexibility of the machine or the inertia of the machine, we cannot operate the machine. In such cases, we need to make small modifications if we simply add masses or springs, we can modify the natural frequencies of the system so that the resonance of the machine is avoided. Troubleshooting and design model analysis is also used is one way of finding out the faults in the machines, because when faults occur in machines, then these faults may change the stiffness of the system or the inertia, mainly the stiffness of the system. So if the stiffness of the system changes, then it will cause change in the natural frequencies. So any change in natural frequency can be reflected in the model test. So if there is any change in the natural frequency of the system, then we can relate it to the possible incipient faults in the machine. Structural dynamic modification, I told you that sometimes we may need to change the dynamics of the machine. One good example is the undamped dynamic vibration absorber, which you might have learned in vibration engineering. It is one example of dynamic modification. We simply add simple spring masses to the system, and it changes the natural frequency of the system at which there was resonance, and at the new natural frequencies we avoid in this way the this phenomenon of resonance. Am I audible? Hello? Okay, thank you. So third is FE model correlation and updating. So this was my title of the presentation, FE model correlation and updating. We can relate the measured natural frequencies with the natural frequencies which we find out from the finite element model. So if the finite element model parameters are good or accurate, then the results will be correlating. But if there is any error in the parameters of the model, then the results of the finite element model will not match with the experimental results. And what is considered correct, the measured results are considered correct. Okay, experimentally obtained results are considered correct. So if there is any change in the results, then what we do, we try to find out the areas of uncertainty in the parameters, and we select some parameters and we make changes in those parameters and try to match the FE model natural frequencies or the models with the measured values. Okay, so this I told you, structural health monitoring is also one application of model testing. Okay, so this window I told you. Now with some experimental studies, I will explain you this the concept of experimental model analysis and the concept of finite element model updating. So before that, I should tell you that finite element model updating in itself is a big area of research, and students, you might not be knowing about this term, the finite element model updating, but in itself is taught as a subject in some institutes like IIT Delhi, and there are many methods which are proposed by researchers to update the finite element models. Okay, structures, spinning structures like rotor systems. So here I have taken one example of experimental rotor system. This is one experimental rotor system. This rotor is mounted on the two ends by rolling element bearings, and in the middle there is a disc. This is a single disc rotor system, and these are the magnetic bearings. At that time there was some other experiment going on, so but in my work these magnetic bearings were not used. So what we do here, what is finite element modeling? This is a schematic diagram how we are mathematically modeling this system. So the bearings, the two bearings are modeled by these spring damper systems. One is a helical spring and damper system, one is a spiral spring and damper system. Okay, and these are the lengths and diameter of the disc here. So this shaft is discretized here into many elements, like you can see here. These are the nodes of the elements. So there are total 28 elements, 28 nodes, so 27 elements. Two-noded beam element was used for this work. So okay, so you can see here this blue colored line points the FE mesh, the red colored points show the measurement points. Okay, and these 0.1 and 0.28 shows the bearing points, and these points are listed here. Okay, so both studies were carried out here using the theoretical model analysis. Theoretical model analysis for this work was done in MATLAB. MATLAB code was written for finding out the theoretical natural frequencies in mod shapes. And for the model testing, impact hammer was used and eddy current probes were used for the model testing. So you can see here, when we make finite element model of any system, we take the data from the data book. Like if you are using steel for some components, so you take its mass density and elastic constant from the data book. But modeling supports or the bearing is not as easy as modeling the material inertia and material flexibility, because we do not know anything about the flexibility that is provided by the supports at the two ends by bearings. So this is one area of research where we also said joint modeling and joint model updating. So here the springs are modeled by these springs and dampers, both helical springs and spiral springs and dampers, and we start with some initially taken data. So from the available results, so this data is taken here, the vertical stiffness and the horizontal stiffness, direct stiffness we say it, and the tilt stiffness. So the direct stiffness and tilt stiffness, angular stiffness. So we are modeling these by angular spring. So its stiffness is given by, here for example, 1 into 10 to the 6 Newton meter per radian. The damping is given by 10 Newton meter per radian, 10 Newton meter second per radian. Okay. So now disk was modeled in SolidWorks to find out its inertia properties. So mass, diameter mass moment of inertia and polar mass moment of inertia has been taken here. And next, this table shows the results of the this table shows the measured results, measured eigenvalues, and this table shows the eigenvalues found out from the finite element model. So you can see here that I started with some data, initially taken data. I didn't know anything about these parameters, so I started with some values, and you can see here that in the first mode, the natural frequency is 23.75 hertz, whereas the corresponding mode from the finite element model is found out at 43.36. Okay, and percentage difference you can see here in various modes. This is the percentage difference. So you can see here the error in the natural frequencies is 82.57. The error is very high because I didn't know anything about the bearing parameters, and the error in damping is more high. I should tell you one thing here, that modeling stiffness is easier than modeling damping in any system. So here you can see both measured and real, measured real and imaginary parts of the eigenvalues are smaller than the values of the initially FE model. You can see natural frequencies are higher here from the FE model, and the natural frequencies are smaller here from the measured values. It shows that the stiffness that is considered in the finite element model must be high, because the simple expression of the natural frequency is under root k by m. If the stiffness is high, then we will have the value of the natural frequency to be higher. So this gives one idea that what is the pinpoint here, that we should target the stiffness for the updating, right? So sensitivity analysis for selection of updating parameters. Now, what parameters should be considered for updating? Like in this simple example also, there are so many parameters: 1, 2, 3, 4, 5, 6, 7, 8, and even internal damping 9. 9 parameters are there, but considering many parameters is not correct. So we should select the parameters which are which should be updated. So for that we carry out the sensitivity analysis. So in sensitivity analysis, what we do, we find out sensitivity of the parameters, and we can find out eigenvalue sensitivity. So selection of updating parameters is an important step in the updating process. Sensitivity analysis of eigenvalues with respect to system parameters helps in selecting updating parameters. So what we do here, we find out sensitivity of different eigenvalues with respect to different updating parameters. So based on the sensitivity analysis, these parameters are considered ky by theta tilde stiffness in y direction and z direction, tilt damping or angular damping in y direction and z direction, and the shaft material damping. And based on these parameters, some objective function is formed. I should tell you at this point that in literature there are various methods. Like one method is based on the eigenvalues, where we compare the natural frequencies, measured natural frequencies, with the FE model natural frequencies, and from there we form some objective function. Here the same method is used. What we have done here, first we wrote one vector where the first 8 natural frequencies were considered from the finite element model, and we took its difference from the first measured natural frequencies of the finite element model. And that difference, you could see that from the table that difference is high. So one method, that is inverse eigen sensitivity method, is used in this method, in this process, in which over a number of iterations we find out the percentage deviation, percentage correction, and we make changes in these parameters, these bearing parameters, the tilt parameters, stiffness and damping, and the material damping. And after updating, before updating, these parameters had these values, and after updating, these parameters have these values. Okay. And after updating, you can see that from this table, before updating, this natural frequency was coming out to around 43 Hertz, and error was very high. So after updating, you can see the error in the natural frequency is very small, even less than 1% in many modes. Okay, and error in damping in few modes is small, but in higher modes there is error. But I told you initially that modeling damping is much more difficult because there are many damping models, but modeling stiffness is easier. So you can see that the updating method updated both real and imaginary parts of the eigenvalues well. Error in real part of the eigenvalues is more in comparison to error in the imaginary parts, and modeling damping is difficult. This is how the error has converged. Initially the error was high, but as we update over the many iterations, after 30th iteration, the values are found out such that the error in the various modes is very small. Okay, error in natural frequencies is plotted here, error in damping factors is plotted here. Okay, am I audible? Hello?
Yes, sir. Yes, sir.
Yes, sir. Audio.
Okay. Now, once we have such correlation, then it gives us confidence that yes, the finite element method can be used reliably to predict the actual results. Okay, so once we have such results, we can say that we can use the finite element model reliably for prediction of actual in the field, for prediction of results in the field. Okay, now we can use one correlation is given here. So this was the how to correlate. This is one plot where this is the plot of the transient are the peaks corresponding to various natural frequencies, and the red colored plot here is the frequency response function that was plotted from the initial model before updating, and you can see there is so much difference between the peaks and also in the amplitudes. Now after updating, you can see once the model is updated, this black colored plot is for the measured results and the red colored plot is for the updated model results. You can see that how closely the results of the frequency response function from the two approaches are matching here. Okay, and in this model there was some noise, and this noise was eliminated by some method. This was proposed by these researchers like Stanley, Turk and Kakar in 2005. So when we eliminate the noise, this is the overlay of the frequency response functions. So you can see here natural frequencies updated very closely, peaks are matching, even the amplitudes are very close to the measured amplitudes. So these are the conclusions of this study. The model updating method updated the initial model well. So this, I should tell you at this point that this finite element model updating is an area of research, and still many people are working to find out various methods, because one method cannot be applied to update finite element model of all the structures. Like the methods which are there for structures, non-spinning structures, cannot be applied for the model updating for spinning structures. Okay, so for rotating machines we have different methods, because in rotating machines the principle of reciprocity does not hold. Okay, so natural frequencies were updated very closely with the measured values, and there is error in damping estimates, and it is found more in higher modes. In lower modes are updated more closely than the higher modes, and proper damping modeling is difficult. The updated model predicted, measured transient and frequency response quite correctly. Now, there I have few more plots. So I will be talking few things about the rotor dynamics. Okay, what is the difference between non-spinning structure and spinning structure? You know that natural frequencies are the properties of system, and natural frequencies are not dependent on the system's inertia and system's flexibility. Natural frequency, the formula of natural frequency is under root k by m. So if k is not changing, m is not changing, then natural frequency will not change. But this is not true for rotating machines, because in rotating machines, the rotating machines experience gyroscopic effect. You know, you might have learned this term gyroscopes in theory of machines. The same gyroscopic effect is there in rotating machines. So for rotating machines, the natural frequencies are dependent on speed. So you can see this plot where, as the spin speed is changing, the natural frequency in the various modes has been plotted here. The natural frequency in first two modes, third, fourth mode, fifth, sixth, and seventh, eighth mode. And as we increase the spin speed, the natural frequency in some modes is decreasing, like here, and some modes it is increasing. So here comes the concept of backward and forward modes. Okay, and here the model damping factor has been plotted. So what is the forward mode and what is the backward mode? That I can explain to you, because in backward mode what happens, for example, we are considering a single disc with a rotor shaft with a single disc. So when it is backward mode, then the direction of the whirling. What is whirling? Whirling is a phenomena where the bent axis of the rotor shaft spins with the spin axis of the rotor shaft. Okay, this is whirling. When the whirling direction and the direction of spin is same, then we said forward whirling. When the whirling speed, whirl direction and the spin direction are different, then we said backward whirling. So natural frequency in backward modes always decreases, and natural frequency in forward modes always increases. Why this natural frequency is getting affected? What is changing out of k and m? You know, inertia does not change, and rotating machines inertia does not change, but this gyroscopic effect causes change in the stiffness of the system. So for example, in the backward modes it is causing decrease in the stiffness, and the forward modes it is causing increase in the stiffness. Therefore the natural frequency in the backward modes increases, and the natural frequency in the forward modes increases, and natural frequency in the backward mode decreases. Okay, so critical speed has been found out here. You can see this is the synchronous whirl line. This line corresponds to the excitation order lines, where the excitation is same as the excitation frequency is same as the spin frequency. Okay, and when does it happen? So rotating machines have various types of faults. Rotating machines have various types of faults, like unbalance is the primary fault, and other faults may also be there, like rotor brake, misalignment. So under different faults, various types of excitation frequencies are there. But unbalance is one excitation which is associated with the synchronous whirl excitation. That means the frequency, the whirling frequency will be same as the spin frequency of the shaft. Okay, so when this synchronous whirl line intersects with the forward mode in any of the modes, then that intersecting line, that point is called the point corresponding to the critical speed. You can see the critical speed of this rotor system is found out to be 1447 rpm. Okay, and similarly we can find out the stability limit speed for the rotor systems. Okay, just a minute. Okay, so what we do next? What is the just we have been talking about the finite element model updating. Just I should recall to you that what is the importance of finite element model updating. Once we update the finite element model, we can use that model even for the prediction of faults in machines. You have been attending few more lectures on condition monitoring of machines. Like one was here by Professor Kakar, one will be tomorrow by Professor Mane Patil, and one more lecture by Dr. Gangsar. So, but this model testing can also be used for fault identification. Okay, and for fault identification, we should have accurate finite element model. So here lies the importance of finite element model updating. So in this study, what we had been done, the rotor shaft system, single disc rotor system is used for the balancing. Even we use the finite element model that I told you for balancing of the rotor system. It is assumed that the unbalance is present in the disc only, so it is single disc balancing. Okay, the updated model is used to find out the unbalance in the system by minimizing the difference between the initial unbalance response and from the measurement and the updated model. The unbalance predicted is then used to get the balancing mass. So what we have done, I told you the single disc rotor system, and it was unbalance disc. Okay, so we found out the unbalance, measured unbalance here, like at 910 rpm, this is the response that was measured, and then we used that finite element model such that we have to minimize this unbalanced response. This should be ideally this should be zero, but no rotor system can be fully balanced, and some residual unbalance will always remain in any system. So we tried to minimize this. We set some objective function where we said that this should be zero, and then over many iterations we found out that the predicted unbalance is 0.00157 kg in the disc that we considered. The balancing mass is 28.6 gram at 55 millimeter radius. When we set that balancing mass in the disc, you can see here that this was initially measured unbalance, and red colored one is the response after balancing, and this was the overlay that was made to find out the location of the heavy spot. Okay, so in this way use of the updated models is shown to find out unbalance in the rotor system. Okay, so conclusions: FEM is used in many areas of engineering for static as well as dynamic analysis. Convergence check is necessary to rely on FEM results. Models should be checked in the light of experimental results, and in case of deviation of FEM results with measured results, the model should be updated. So at the end, I should say that whenever we carry out finite element studies, finite element model studies, the first thing is that we should check it for convergence, and if possible, we are going to use the results. And if we can conduct some dynamic test, if we have those facilities, then we should carry out few dynamic tests like for the estimation of natural frequencies, and then we should compare the natural frequencies, the FE model natural frequencies with the measured natural frequencies, and if there is any, if there are high differences, then we should try to select some parameters which you think that may have errors, and then we should try to adjust. You can do it by hit and trial method also. I use one established method, which is their inverse eigensensitivity method for the finite element model updating. So this was all about this study about checking accuracy of the finite element models. Now we can take questions.
Okay.
Or I can show you some more slides if you wish on the rotor dynamics. Okay. or we can take questions now.
Any questions from audience? Subodh, any questions from YouTube or Google chat?
No, sir, I can't find any questions from YouTube yet. Mr.
Yes.
Professor Jani is saying something. Okay.
Hi, thank you, Dr. Chokse, for your informative talk. And I really appreciate that you have taken time, even after the connection issues, you have reverted back and finished the talk. I have one question. You have shown that you were able to match the peaks of the frequency response function pretty well because you were having a good estimate of the natural frequencies, but you were not able to match the peak widths because the estimation of damping was horrible. It was very poor, 100% deviation in damping. I am aware that people are working on modal damping with fractional order derivatives. Like people have not struggled on loop-rate system models, but they are not very good for modal damping of rotor dynamic systems. So have you seen some fractional order damping models which are discrete damping models for that specific mode? Would you like to share some information on that?
Yeah. See here, like I told you that modeling stiffness is easier, very easier. We should say that than modeling damping, because for damping there are so many models: linear models, non-linear models. Okay, and simple damping model we use generally. So in this study, viscous damping model was used, proportional damping, where the damping force is proportional to the velocity. But we need to consider, if we have to match the peak amplitude of the FRF, then we need more frequency models, more damping models. We have to incorporate in the system. Well, here a simple damping model was used, so error was high. But this is one area where different damping models can be incorporated in the finite element study, and then we can compare the results of the measured peaks with the corresponding FE model peaks. And I'm sure that if you are working on some damping model and if you relate it, with the FE model results, then it may give better estimates of the damping. But in all, I am not sure, because a single damping model may not be sufficient. Sometimes you may also use to incorporate one or two or more damping models in the same system, because damping is a complex phenomena, and just we cannot say that simple one mechanism is involved here, because when bearing damping is there, we consider bearing damping in this study. We consider soft material damping also, but for both the cases, simple viscous damping model was used. Okay, and hysteresis we didn't consider. Hysteresis damping we didn't consider, so that damping model can also be considered here. Static damping.
Yeah, I understand. I have struggled with damping models for around 3.5 years in my career. So maybe that is one area where maybe we can meet and collaborate and do something, because I have some ideas about damping models, and which is and I saw that it was very primitive in your model. The other thing which I wanted to ask is you have considered a baby problem, just one rotor on a shaft, and did model testing, because your aim was more to kind of show the demonstration of the concept or proof of the concept. But for a more complex system, what I mean is that here you had 3 or 4 parameters which you were varying, and closed form analytical expression is also existing. So frankly speaking, you don't even need finite element model updating, but it's more for the proof of concept. But what I wanted to ask is, suppose for a more complex system, if you want to do FE model updating, then there are conflicting parameters. Suppose if you choose 3 or 4 parameters, then you have to do Pareto front and do Monte Carlo simulation to get that. So how do you incorporate constraints in that? Because sometimes what happens is that even with Lagrange multipliers, one of the it kinds of saturates one of the parameter and neglects all other parameters. So do you have encountered some kind of this kind of problem in your in other PhD study, like apart from this? This is a simple one, but you might have worked on complex models.
Yes, definitely. So first thing is that in this method, I had developed one method during my PhD study, and for damping of rotating systems. So that I demonstrated here. So about the number of parameters that we can consider, I should tell you that really it is very difficult to select the proper parameters because there are so many parameters. Then and we if we consider all the parameters, then the algorithm may be as unstable. So how does it come to select the proper number of parameters, or the how to select a particular parameter and how to means not select some other parameters? How that comes, I will tell you that, because during my study I found out that in this problem, what is the most handy thing, or what becomes useful is the knowledge about the structure, because ultimately what we are doing, we have considered some actual structure, and we have developed some finite element model for that system. So knowledge about the structure is the first and foremost thing. And when we work on the structure, okay, and that engineering judgment comes from knowing the structure. Like when we work with some structure, we know about it, we know what are various parameters that can be considered, and over the time and with experience, that thing comes that this, if I select this parameter, then it will be going to give me more accurate results than considering some other these parameters. And the one more thing is that I told you in the study, that sensitivity analysis. Eigenvalue sensitivity analysis is also helpful in selecting the number of parameters, because if in some for some parameters the eigenvalue sensitivity is low, okay, the eigenvalue sensitivity is low for some parameters, then it is not wise to consider those parameters, because ultimately the corrections will be small or negligible in those parameters, right?
Yeah, I understand. My question was a little bit more complex than what, but we can talk offline. I don't want to waste time of other participants in this question. Maybe we can chat over mail or something. Okay.
Sure. Sure.
Thank you.
Message box. Captions. Captions now.
Subodh having some questions from YouTube chat and Google chat.
Yes, sir, I've noted the questions. The first one is from Mr. Alok Kumar, that what are the main reasons of mismatch of results in experiment and theory?
Okay. Main reasons of mismatch, I told you that in the presentation, that modeling flexibility, like elastic constant, most of the materials we know, models of elasticity is responsible, or this models are responsible for the flexibility in the system. If we torsional rigidity constant it is responsible for torsional flexibility. The elastic constant is responsible for bending elasticity. So we know very well these elastic constants. So there are less chances of any error. Okay, and when we consider inertia, then we very well know now the mass properties of the materials. So there are less chances or almost no chances of error in these parameters. Where the error comes, like if we talk of structures like car body, we are using various joints. If we are modeling, we are developing some model of the car body. The various joints are used here at various places, but we don't know the flexibility of those joints. So here comes the importance that we are making some finite element model and we want to correlate the results with the measured results. Then these joints contribute to the errors. Joints may contribute to the errors in the model, and this is one area where people are working: joint model updating. Updating of the finite element, joints of the finite element model, and bearing parameters. Bearing also is one example of joint. We can say, okay, we have some connection there. So bearing parameters also need to be updated. Okay.
Okay, thank you, sir. Our next question is that what are the softwares used to FEA in mechanical engineering field, and is there any easy or standard software for that?
For model analysis, I use means if I use ready softwares like ANSYS, I use ANSYS APDL, ANSYS Workbench. Okay, and if I write code, then I use MATLAB. But when I would like to comment on ANSYS Workbench and ANSYS APDL. So ANSYS Workbench is used more nowadays, I think. But and what people do is they just create some solid model of the structure and carry out the result. But it is always not desired for simple vibration problems like where we can model the structure by beams. We do not need to take 3D elements, just beam elements is sufficient. So here we should use the ANSYS APDL instead of ANSYS Workbench. We should work on ANSYS APDL because this is my experience that working with line body elements, simple beam elements is more difficult with ANSYS Workbench, and it is easier with ANSYS APDL. Okay.
Thank you, sir. Another question is from Mr. Alok Kumar that while simulate the physics by FEM, it's highly dependent on meshing. So could you
Yes.
comment on it with modal as well as transient analysis?
Yes, FEM, we study here the dynamic analysis we carried out with this method, find element method. Okay, and it is dependent on meshing. Definitely, it is dependent on meshing. But I use simple structure shaft, so the meshing was not so complex. Okay, but then I told you about the convergence check. We should carry out the convergence check before relying on the results of the find element method. Okay.
Okay, sir.
Meshing,
Another question.
but when we do with other solid models like some complex solid, then the issues of meshing are more complex. But then there, the one thing is sure you should apply the conversion also. Okay.
Sir, another question is from Purushottam Gangsar, sir. That could you explain forward and backward world?
Yes, sure. So there is shaft, and it is supported on two bearings, and there is disc. Okay. Now shaft is spinning in clockwise direction, looking from any of the end. Shaft is spinning in the clockwise direction, but due to unbalanced forces, what will happen that shaft will bend, and shaft will make some shape like bow. Okay. Now this bow shape, the bend shape, will be spinning also. Now this bend shape may be spinning in the same direction as that of the shaft. Then we say it forward whirl. But if this bent shaft axis even may spin in the opposite direction to that of the shaft spin, that is possible. Okay, and that happens in the actual rotors. In actual rotating machines, this happens that the bent shaft axis or bent shaft, the bent rotor system may spin in the opposite direction to that of the shaft spin. If this happens, then we say it a backward whirl. And I will tell you that backward whirl is considered to be more dangerous than the forward whirl, because in backward whirl, this fatigue loading or the fluctuating, cyclic loading is more than that of the forward whirl. Okay.
Thank you, sir.
Okay.
So, Professor Ganai, should we conclude now? Okay. So, thank you, sir. Thank you, Dr. Manoj Choksey, sir, for accepting our invitation to talk for this presentation. You explained very well on checking accuracy of result of finite element analysis. Very excellent session by you, sir. There are some problems, but it is very well explained by you on various ways of checking accuracy, vibration analysis in ANSYS, classification of analysis, and variation of eigenvalue. And also you concluded that convergence check is necessary to rely on finite element method result. Thank you again, sir. Thank you very much.
Thank you all. Thank you.
For tomorrow's session, we will meet at 11:30 a.m. Thank you, sir.
Okay, thank you.